Gaze up at the night sky, at those pinpricks of ancient light, and tell me you truly know what's out there. We've all seen the footage, heard the stories of heroes and giant leaps, and we think we understand the broad strokes of space exploration. But what if everything you think you know is just the cover of a book filled with chapters so strange, so utterly wonderful, they defy imagination? This vast, silent cosmos holds secrets that challenge our very perception of reality, and today we're going to crack that book wide open. Forget the textbook summaries. We are about to embark on a journey into the heart of the unknown, a voyage through 30 of the most bizarre and breathtaking facts ever uncovered in our quest to touch the stars. These aren't just trivial details, they are testaments to human ingenuity, cosmic oddities, and moments of pure, unadulterated wonder that will leave you seeing the universe in a completely new light. This journey is more than a simple list, it's a story of audacity and awe. It's about the silent tragedies and triumphant quirks that never make the headlines, the peculiar physics that govern the void, and the objects and phenomena so strange they seem ripped from the pages of science fiction. We'll uncover tales of forgotten missions that achieved the impossible, of engineering solutions so brilliantly simple they border on madness, and of cosmic coincidences so precise they feel like the universe itself is winking at us. Every single fact is a thread in the grand tapestry of exploration, woven from equal parts human courage and cosmic mystery. This is the side of spaceflight you never get to see, the hidden narrative that proves the reality of our journey to the stars is often far more incredible than anything we could have dreamed up. So allow yourself to be curious, allow yourself to feel that childlike sense of wonder you might have thought was lost. Because over the next while, we're going to venture beyond the familiar, past the moon landings and the Martian rovers, into a realm where time behaves strangely, where spacecraft carry unexpected cargo, and where the universe reveals its most playful and perplexing secrets. This is an invitation to rediscover the magic and the sheer, jaw-dropping weirdness of space exploration. Prepare to have your mind expanded, your curiosity ignited, and your perception of our place in the cosmos forever changed. The countdown begins now, and that journey into the bizarre begins not with a distant star or a far-off galaxy, but with the human body itself. Our very first fact is a personal one, something every single astronaut experiences, yet it sounds like something straight out of a science fantasy novel. When you leave Earth, you literally get taller. Imagine floating aboard the International Space Station, looking down at our planet and realizing you are quite literally growing out of your own skin. In the microgravity environment of space, the constant downward pull of Earth's gravity simply vanishes. That force is what, down here, compresses the stack of spongy disks between the vertebrae in your spine. With that weight lifted, literally, those discs expand and the vertebrae separate slightly, causing the entire spinal column to lengthen. It's not a sudden, dramatic growth spurt, but a gradual unfolding. On average, an astronaut can gain up to 2 inches in height, transforming them temporarily into a slightly longer version of themselves. This newfound height, however, comes with its own set of peculiar challenges. Think about the meticulous planning that goes into every aspect of a mission. A spacesuit is a custom-fitted, personal spacecraft. It's engineered with specific tolerances for movement and reach. Now picture an astronaut who has grown an inch or two since suiting up for launch. Suddenly, those perfectly tailored gloves might feel a bit tight at the fingertips, and the range of motion in the arms and legs could be subtly different. While missions are designed with some flexibility, this physical change is a constant reminder of the body's dynamic relationship with its environment. But the most profound effect is saved for the return journey. After months of living in a state of elongation, the return to Earth's gravity is a shock to the system. That familiar weight returns and the spine, once again, begins to compress back to its original length. This process can be incredibly painful, causing significant backaches and muscular discomfort as the body readapts to a world where it has to carry its own weight again. It's a strange trade-off, a taste of extra height in the heavens, paid for with aches and pains upon your homecoming. While our bodies stretch and adapt to the freedom of space, the worlds we visit hold their own sensory surprises. After experiencing the strange phenomenon of growing taller, the Apollo astronauts encountered another mystery the moment they returned to the confinement of their lunar module and removed their helmets. It was a smell that none of them had anticipated, an odor that clung to the fine, gray dust coating their suits and equipment. They described it with a surprising consistency. It smelled like spent gunpowder or the scent of wet ashes in a fireplace. Imagine the scene. These pioneers, having just walked on another world, are hit with this pungent, familiar, yet entirely out-of-place aroma inside their tiny spacecraft. It was the smell of the moon itself, a scent conveyed by particles so fine they infiltrated every crease and seam. This bizarre sensory report points directly to the unique nature of the lunar surface. Moon dust, or regolith, isn't like soil on Earth. It's the product of billions of years of bombardment by micrometeorites and constant exposure to solar radiation, which shatters rock into an incredibly fine, jagged powder. It's essentially tiny shards of glass. The leading theory for the gunpowder-like smell involves a process called tribochemistry. In the airless, anhydrous environment of the moon, the surfaces of these tiny dust grains are activated. They have unsatisfied atomic bonds eager to react with anything they come into contact with. For millions of years, there was nothing to react with. But when the astronauts brought the dust into the lunar module and it mixed with the humid, oxygen-rich cabin air, those activated particles underwent a rapid, though minor, chemical reaction. It's thought that the scent is the result of these particles oxidizing, essentially rusting in an instant upon contact with the moisture in the air. The smell of gunpowder we associate with fireworks is also the scent of rapid oxidation, which creates a compelling, if not perfectly exact, analogy. The irony is that this very characteristic that gives the moon its smell also makes it a significant hazard. That sharp, glass-like quality of the dust made it incredibly abrasive, threatening to scratch helmet visors and wear down the seals on spacesuits. More alarmingly, the astronauts reported that the dust irritated their eyes and caused temporary lunar hay fever upon inhalation. The long-term health effects of inhaling such jagged, reactive particles are a major concern for future long-duration lunar missions. So, the moon's signature scent is more than just a curious anecdote. It's a direct, tangible warning of the challenges of living on a world that is not just distant but chemically alien. It's a reminder that every new environment we explore will engage all our senses, sometimes in ways that are as hazardous as they are hauntingly memorable. From the tangible, dusty reality of the lunar surface, our next fact takes us to a creation of pure technological artistry, a satellite that was, in a very real sense, a golden jewel cast into the void. While the Apollo missions brought back the scent of another world, astronomers dreamed of seeing the cosmos in a light invisible to our eyes. This ambition materialized in the infrared astronomical satellite, or IRAS, a pioneering spacecraft that was quite literally plated with gold. But this wasn't an act of cosmic extravagance, it was a stroke of brilliant engineering necessity. To understand why, we need to step into the strange world of infrared astronomy. Every object with even a slight amount of heat, a planet, a dust cloud, even the telescope itself glows with infrared light. If your telescope mirror is warm, it will glow brighter than the faint, distant objects you're trying to see, completely washing out the signal. It's like trying to spot a single, distant candle flame while you're standing right next to a blazing bonfire. The solution was to build a mirror that was an incredibly poor emitter of its own infrared radiation. Gold, as it turns out, is almost perfect for this job. While it's an excellent reflector of infrared light, it's a terrible emitter. By plating the telescope's primary mirror with a thin, flawless layer of gold, engineers created a surface that would barely glow in the infrared spectrum itself. This golden mirror would simply catch the faint whispers of infrared light from the depths of space and reflect them onto the detectors, all while adding almost no interfering heat signature of its own. It was the ultimate cold eye, designed to see the heat of the universe without being blinded by its own. But creating this cold eye was only half the battle. To function, the entire telescope had to be chilled to a temperature just a few degrees above absolute zero, the point where all molecular motion theoretically stops. This incredible feat was achieved by housing the telescope in a giant thermos flask, a dewar or filled with liquid helium. For 10 glorious months, this supercooled liquid kept ERA's golden eye at a frigid -268 degrees Celsius, allowing it to peer into the cosmic dark. And what it saw revolutionized our understanding of the heavens. ERA's was the first mission to conduct an all-sky survey in the infrared, and it revealed a universe teeming with activity that was completely hidden from optical telescopes. It discovered dusty disks surrounding nearby stars like Vega and Fomalhaut, providing the first direct evidence of what are now understood to be planetary systems in the process of formation. It peered through the vast, opaque clouds of dust that block our view of the galactic center, mapping the structure of our own Milky Way in a way never before possible. It identified hundreds of thousands of new galaxies, many of them incredibly luminous in the infrared due to intense bursts of star formation. Perhaps most famously, it discovered something much closer to home, the trail of a comet. This wasn't just any comet. ERA's data, combined with observations from 2 Japanese astronomers, led to the discovery of comet ERA's Araki-Alcock, which passed within 3 million miles of Earth, one of the closest cometary approaches ever recorded. The mission of the Golden Satellite was a spectacular success, a testament to human ingenuity that used a precious metal to unveil the hidden, warm heart of the cosmos, forever changing the landscape of modern astronomy. Our golden-eyed satellite showed us a universe humming with hidden warmth, but if we turn our gaze closer to home, to our own solar system, we find a world that takes the concept of heat to a truly terrifying extreme. Venus, often called Earth's twin because of its similar size and rocky composition, is in reality a twisted, hellish version of our own planet. For decades, scientists viewed it as a geologically dead world, a cautionary tale of a runaway greenhouse effect that had baked its surface to temperatures hot enough to melt lead and crushed it under an atmosphere 90 times thicker than our own. The assumption was that any volcanic activity that once shaped its landscape had long since ceased, leaving Venus a stagnant, fossilized relic. But science has a wonderful habit of upending our assumptions, and recent discoveries have revealed that Venus is not dead at all. It possesses a volcanic heartbeat, a slow, rhythmic pulse of activity that suggests this infernal world is very much alive. The breakthrough came from a painstaking analysis of data collected decades ago by NASA's Magellan spacecraft, which mapped the surface of Venus using radar to peer through its thick, perpetual cloud cover. Researchers were examining a region known as Alta Regio, a vast highland marked by 2 of the planet's largest volcanoes, when they noticed something extraordinary. By comparing radar images taken 8 months apart, they spotted a change. A specific volcanic vent had clearly expanded and changed shape, and a new lava flow had appeared on its slopes. This wasn't the slow erosion of millennia. This was geological change happening on a timescale of months, a clear indication of a fresh volcanic eruption occurring while Magellan was in orbit. Imagine the significance on a world where the surface pressure is equivalent to being nearly a kilometer deep in Earth's ocean, and where temperatures hover around 460 degrees Celsius, molten rock was still forcing its way to the surface. This wasn't an ancient feature, it was a planetary event, a signal that Venus's internal engine is still running. This discovery fundamentally reshapes our understanding of how rocky planets evolve. Earth is tectonically active, with its crust constantly recycled, and Mars shows evidence of massive but now extinct volcanoes. Venus now presents a third model, a planet that is volcanically active but may lack the plate tectonics that drive activity on Earth. Its heat might be escaping through periodic, massive outbursts rather than the continuous, global process we see here. This volcanic heartbeat model suggests that Venus releases its internal heat in dramatic, sporadic pulses, which could explain why its surface appears both geologically young in some areas and ancient in others. It forces us to ask new questions. What is the frequency of this pulse? Are we seeing a regular cycle or random, catastrophic events? The answer holds implications not just for Venus, but for our search for life beyond Earth. While the surface of Venus is unquestionably lethal, its thick cloud decks at an altitude of about 50 kilometers have temperatures and pressures surprisingly similar to Earth's surface. The detection of phosphine gas in these clouds, a potential biomarker, remains a topic of intense debate. But if Venus is volcanically active, it could be supplying chemical nutrients from below into those temperate cloud layers, providing a possible energy source for any hypothetical, extremophile microbial life floating high above the scorching surface. The discovery of a changing vent on Venus does more than just mark a dot on a map. It reanimates a world we thought we understood, turning a symbol of planetary death into a new frontier for understanding the dynamic and potentially life-hosting capacity of rocky worlds throughout the cosmos. From the volcanic pulse of our closest planetary neighbor, we now cast our gaze outward to a true titan of the solar system, a feature so vast it has been a constant in our telescopes for as long as we have pointed them skyward. Jupiter's Great Red Spot is not merely a storm, it is a monument to atmospheric fury, an anticyclonic maelstrom that has raged for at least 350 years and possibly much longer. To grasp its scale, picture this. At its peak, this swirling tempest was so wide that you could have lined up 2 or even 3 planet Earth side by side within its swirling, brick-red borders. It is a permanent hurricane, but one that makes any storm on our world seem insignificant, fueled not by warm ocean waters but by the deep, churning internal heat of the gas giant itself, a planet still cooling from its formation billions of years ago. For centuries, it was the one unchanging landmark on Jupiter, a colossal eye staring out from the bands of the solar system's largest planet. But this iconic feature is undergoing a profound transformation, one that has astronomers watching with a mixture of fascination and a touch of cosmic melancholy. The Great Red Spot is shrinking. Continuous observations, especially from spacecraft like Voyager and the Hubble Space Telescope, have documented a steady decrease in its diameter. Where it once could have easily swallowed our entire planet, it is now perhaps only a single Earth in width. The rate of this shrinking isn't constant. It seems to be tapering, sometimes slowing, but the overall trend is unmistakably downward. This isn't just a change in size. The storm appears to be becoming more circular, losing its distinct oval shape, and there are indications that its winds might be speeding up at the edges as it condenses, like a spinning ice skater pulling in their arms to rotate faster. The question, of course, is why? What could possibly be causing a storm that has persisted for centuries to slowly, steadily fade away? The answer lies deep within the complex and largely hidden atmospheric dynamics of Jupiter. Unlike Earth, Jupiter has no solid surface to disrupt weather patterns. Its atmosphere extends for thousands of kilometers, a fluid canvas of ammonia, water, and hydrogen. One leading theory suggests that the Great Red Spot is interacting with smaller storms and jet streams that flow around it. These smaller eddies, while insignificant in size compared to the spot, might be acting like atmospheric sandpaper, gradually eroding its edges and stealing its energy, causing it to lose momentum and contract. Another, more intriguing possibility delves into the very heart of the storm itself. The Great Red Spot is not a superficial feature. It is thought to be a deep-rooted structure, perhaps extending hundreds of kilometers down into the planet's interior. The shrinkage we witness on the cloud tops could be a symptom of changes happening far below, in the mysterious transfer of heat and energy from Jupiter's core. It's possible that the internal engine that has sustained this storm for so long is simply running out of fuel, or that shifts in the planet's deep thermal currents are slowly strangling it. Watching the Great Red Spot diminish is more than just observing a change in weather. It's like watching a chapter of solar system history slowly close. Its longevity has been a fundamental puzzle for planetary scientists, offering a unique window into the fluid dynamics of gas giants, both in our own system and in the countless exoplanets we are discovering around other stars. Understanding why it is fading could teach us about the lifespan of such massive atmospheric features and the ultimate fate of the dynamic systems that power them. While predictions are difficult, some models suggest it could become circular within a few decades and might even disappear entirely within our lifetimes, transforming from a defining landmark into a historical footnote. This gradual vanishing act serves as a powerful reminder that even the most permanent-seeming features of our cosmos are transient, caught in their own cycles of birth, evolution, and decay, playing out on a scale that both humbles and enthralls us. If the silent, fading storm on Jupiter evokes a sense of cosmic quiet, then our next fact shatters one of the most deeply ingrained myths about space itself. We are taught from childhood that space is a perfect vacuum, and in the vacuum there is no sound. It's a chilling thought, a universe of complete and utter silence, where stars explode and galaxies collide without ever making a whisper. While it's true that the familiar sound waves we experience on Earth, which rely on a medium like air or water to vibrate, cannot travel through the near-empty void, this doesn't mean space is entirely mute. It's simply that our human ears are not equipped to hear the symphony that is actually playing all around us. The cosmos communicates not through pressure waves in air, but through an invisible sea of energy and particles, and with the right technology, we can translate that cosmic chatter into sounds we can understand. This translation process begins with the discovery that space, far from being empty, is filled with a tenuous, superheated gas known as plasma. This fourth state of matter, where atoms are stripped of their electrons, is electrically charged and therefore highly responsive to magnetic fields. Throughout the solar system, planets with magnetic fields like Earth, Jupiter, and Saturn create massive, invisible structures called magnetospheres. These act like protective bubbles, deflecting the constant stream of charged particles flowing from the sun, the solar wind. The interaction between the solar wind and a planet's magnetosphere is anything but quiet on an electromagnetic level. It creates oscillations and vibrations within the plasma itself, generating what are known as plasma waves. These are not sound waves, but rhythmic variations in the density and magnetic field of the plasma that can be detected by sensitive instruments on board spacecraft. This is where the magic happens. Scientists can take the data from these instruments, the frequency and amplitude of these plasma waves, and shift them into the range of human hearing. It's a process called sonification, akin to how a radio receives electromagnetic waves and converts them into music. What emerges from this data translation is not the whoosh of a spaceship from a movie, but something far more alien and profound. The results are some of the most haunting and beautiful sounds in the solar system. The Cassini spacecraft, as it flew through the environs of Saturn, recorded the intense plasma waves generated by the interaction between the solar wind and the giant planet's magnetosphere. When converted, these recordings sound like an eerie, ghostly chorus, a symphony of shrieks and whistles that scientists aptly named the Saturn Chorus. Similarly, the Juno spacecraft has captured the tumultuous sounds generated by Jupiter's colossal auroras, resulting in a series of crackles, pops, and deep, booming surges that convey the raw power of the gas giant's magnetic field. These audible translations are far more than just a novelty. They are a powerful scientific tool. By listening to the data, researchers can sometimes identify patterns and features that might be less obvious in visual graphs. The complex interactions within a planet's magnetic environment create distinct acoustic signatures, allowing scientists to diagnose the health and dynamics of that system. It gives us a new sense with which to perceive the cosmos, turning abstract data into an experience that feels almost visceral. So, while an astronaut floating outside their spacecraft would not hear the roar of a passing comet or the hum of a distant star, the universe is far from silent. It is a vibrant, dynamic arena filled with electromagnetic music, a grand opera played on instruments of plasma and magnetic fields, waiting only for our technology to give it a voice. This revelation transforms our understanding of the void from a place of absolute quiet to one of vibrant, if imperceptible, activity, reminding us that the cosmos is alive with energy, resonating in a key we are only just beginning to hear. From the haunting electromagnetic chorus of our own solar system, we now turn our attention to a distant star system where an entire world defies the very definition of a planet. Imagine a celestial body so dense, so extreme, that its primary geological feature is not silicate rock or iron, but a lattice of crystallized carbon. Scientists have discovered a planet that is, in all likelihood, a colossal diamond orbiting its sun. This isn't science fiction. It's the incredible reality of an exoplanet known as 55 Cancri e, located about 41 light-years away in the constellation of Cancer. The story of this world begins not with what we can see directly, but with what we can deduce from the subtle dance of its parent star. 55 Cancri is a binary star system, and around one of these suns, astronomers detected the telltale wobble caused by the gravitational tug of an orbiting planet. Further observations with the transit method, which measures the dimming of a star's light as a planet passes in front of it, revealed the planet's size and orbital period. The data painted a picture of a super-Earth, a world with about twice the diameter of our own and over 8 times its mass, but orbiting so close to its star that a single year there lasts a mere 18 hours. The truly revolutionary discovery, however, came from modeling the planet's composition based on its mass and radius. These calculations revealed an astonishingly high density, which pointed to a chemical makeup utterly unlike Earth. Our planet is rich in oxygen, silicon, and magnesium, but 55 Cancri e orbits a star with a high carbon-to-oxygen ratio. The prevailing theory suggests that under such conditions during the planet's formation, carbon would have been a dominant building block. The immense gravitational pressure at the planet's core, combined with scorching surface temperatures estimated to be around 2,400 degrees Celsius, creates the perfect crucible for a remarkable transformation. Just as coal transforms into diamond deep within the Earth under immense heat and pressure, but on a planetary scale, the carbon within 55 Cancri e is thought to have crystallized. This isn't a surface covered in sparkling gems. The entire planet, or at least a significant portion of its interior, is likely a single, massive diamond-like structure. But what would such a world actually be like? The imagery of a glittering jewel floating in space is captivating, but the reality is far more alien and hostile. This diamond world would not have a solid surface in the way we understand it. While its interior may be a crystalline lattice, the surface itself is likely a terrifyingly dynamic place. With such a close orbit, the planet is probably tidally locked, meaning one side permanently faces the star in perpetual, scorching daylight, while the other is locked in eternal, frigid night. Some models suggest the sun-facing hemisphere could be a global ocean of superheated lava, constantly churned by gravitational tides. Other theories propose that the planet might be venting atmospheres of vaporized rock, creating a thin but searing envelope of silicon-based gases. So, rather than a pristine, faceted gem, 55 Cancri e is more accurately envisioned as a core of unimaginable diamond wealth, shrouded in a hellish shroud of molten rock and vaporized minerals, a testament to the universe's ability to create beauty forged in the most extreme conditions imaginable. The existence of such a carbon-rich world also forces us to broaden our perspective on planetary diversity and the potential for life. For a long time, the search for habitable worlds focused on finding Earth twins, planets with a similar balance of water and rock. The discovery of diamond planets like 55 Cancri E reveals a whole new class of worlds, carbon planets, which could be far more common around stars with a high carbon abundance. While 55 Cancri E itself is clearly uninhabitable, the concept of carbon-based planets existing throughout the galaxy opens up fascinating, if speculative, possibilities. Could there be cooler carbon planets with surfaces of graphite or even more complex carbon compounds? The element carbon is, after all, the foundation of life as we know it. While a diamond planet is a sterile monument to extreme physics, it reminds us that carbon is a versatile cosmic ingredient, capable of forming both the basis of life and the most dazzling of geological wonders. The discovery of 55 Cancri E challenges our planetary prejudices, showing us that the universe is not limited to creating worlds like our own, but can forge realms of pure crystal, expanding the catalogue of cosmic possibilities in ways we are only beginning to comprehend. This journey from the fantastical to the practical brings us to a technology that is as vital as it is viscerally challenging, a system that turns one of the most basic human functions into a cornerstone of survival far from Earth. On the International Space Station, every single drop of water is precious. Resupply missions are expensive and infrequent, making it utterly impossible to simply ship up enough water for a crew of 6 or 7 astronauts for months on end. The solution to this problem is a masterpiece of closed-loop engineering, a system that recycles about 98% of the water on board. And this process includes a step that always captures the imagination. Astronauts drink water that was, quite recently, their own urine. Now, before you recoil, it's crucial to understand that this isn't a simple filtration. It's a multi-stage purification process so rigorous that the resulting water is actually cleaner than what most of us drink from the tap here on Earth. The journey of a droplet begins with collection. The Water Recovery System, or WRS, gathers water from several surprising sources. It captures humidity from the crew's breath and sweat, condensing it out of the cabin air. It also collects water from shower runoff and from the station's hygiene station. And yes, it collects urine. These waste streams are then fed into the heart of the system. The first major hurdle is dealing with the urea in urine, which breaks down into ammonia and can be highly corrosive. The system uses a process called vacuum distillation. The urine is spun in a centrifuge under a partial vacuum, which lowers its boiling point. It's then warmed slightly, causing the water to evaporate out, leaving behind a concentrated brine of waste products. This water vapor is then condensed back into a liquid, but this distilled water is still not pure. It contains traces of chemicals and volatile organic compounds that evaporation alone cannot remove. This is where the technology becomes truly remarkable. The next stage involves pushing the distilled water, along with all the other collected condensate, through a series of filters and a catalytic reactor that would be more at home in a high-tech chemical plant. The water is forced through multi-filtration beds containing substances that absorb or cling to any remaining contaminants. Then, it enters the oxygen generation system, where it is electrolyzed, split into breathable oxygen for the crew and hydrogen, which is vented overboard. But for the water destined to be drunk, the final and most critical step is the catalytic reactor. Here, the water is combined with oxygen and heated to over 130 degrees Celsius, a temperature that would cause it to boil violently at normal pressure. But because the system maintains high pressure, the water remains a liquid. In this superheated, oxygen-rich environment, any lingering organic impurities essentially, the last vestiges of what made it waste are completely oxidized, broken down into harmless carbon dioxide and water. The result is water of exceptional purity. So, what does this recycled water actually taste like? Astronauts consistently report that it tastes perfectly normal, like any bottle of still water. There is no off flavor or reminder of its origin. In fact, the water is so pure that minerals have to be added back into it for two important reasons. First, it improves the taste, as completely pure water can taste flat to our palates. Second, and more importantly, the crew needs those electrolytes for their health. This entire intricate process is not just about overcoming the Ike factor. It's a non-negotiable requirement for the future of space exploration. A mission to Mars, for instance, would be impossible without such a robust recycling system. The amount of water required for a crew for a journey that could last up to 3 years is simply too massive to launch from Earth. This technology transforms the spacecraft from a mere vehicle into a miniature, self-sustaining ecosystem where waste is not disposed of but repurposed into a vital resource. It's a profound demonstration of a key principle for living beyond our planet. In space, there is no such thing as waste, only raw materials waiting to be reclaimed. We just explored how human ingenuity transforms waste into a vital resource aboard the International Space Station, a testament to our ability to create sustainable systems in the void. But when we look up at the source of nearly all energy in our solar system, we encounter a mystery that has stubbornly defied our understanding for decades, a paradox of physics happening right in our own cosmic backyard. It concerns our sun and a simple, logical assumption that turns out to be completely wrong. If you were to take a journey from the center of the sun outward, you would expect the temperature to get progressively cooler, right? Just like moving away from a campfire, and for the most part you'd be correct. The core, where nuclear fusion rages, is an unimaginable 15 million degrees Celsius. The surface, called the photosphere, is a much cooler 5,500 degrees, still hot enough to vaporize any material we know. But then something utterly baffling happens. As you move away from the surface into the sun's wispy outer atmosphere, the corona, the temperature skyrockets again, soaring to a blistering 1 to 2 million degrees Celsius. This is the coronal heating problem, and it's one of the most enduring and perplexing puzzles in all of solar physics. Think about how counterintuitive this is. It's as if you walked away from a blazing oven and a few feet past it stepped into an inferno that was hundreds of times hotter. The corona is the beautiful, pearly white halo of plasma that becomes visible during a total solar eclipse, a structure that extends millions of kilometers into space. For a long time, astronomers couldn't explain why this tenuous, distant atmosphere was so incredibly hot. The mystery only deepens when you consider the energy transfer involved. Heating the corona isn't like heating a pot of water on a stove. The corona is so diffuse that it has very little actual matter to heat. If you could somehow stand within the corona, you wouldn't feel the intense heat in the way we feel it on a hot day because the particles are so far apart. The temperature here refers to the particle's average kinetic energy or speed. These particles are moving insanely fast, but there just aren't many of them in a given space. The real question is, what force is injecting so much energy into these particles to make them move that fast, especially when the energy source, the sun's fusion engine, is 93 million miles away with a much cooler layer in between? Scientists have been grappling with this for over half a century, and the prevailing theories point to two main suspects, both involving the sun's complex magnetic field. The first is known as nanoflare heating. The sun's surface is a turbulent sea of plasma, and its magnetic field lines are constantly being twisted, stretched, and tangled by the churning motions beneath. Imagine millions of tiny, tangled rubber bands building up stress. When these magnetic field lines suddenly snap and reconnect into a simpler, less stressed configuration, they release a tremendous amount of energy in a kind of miniature explosion. We see large versions of these as solar flares. The theory suggests that the corona is being heated by a constant, universe-wide rain of these tiny, undetectable nanoflares. Each one is too small for our telescopes to see individually, but collectively they could provide the steady, pervasive heat needed to explain the corona's immense temperature. The second leading theory involves powerful magnetic waves. The Sun's convective zone just below the surface is like a giant pot of boiling water, and this constant bubbling generates powerful waves that travel outward along the magnetic field lines that arc through the corona. One type, called Elfvane waves, are essentially ripples in the magnetic field itself, similar to how you can send a wave down a length of rope by flicking it. These waves carry energy from the Sun's interior up into the corona. As they travel through the increasingly rarefied atmosphere, they can grow in amplitude and eventually break, much like an ocean wave crashing on a shore, dumping their vast energy into the coronal plasma and heating it. It's likely that both nanoflares and magnetic waves work in tandem to solve this cosmic mystery, with one mechanism dominating in certain regions of the corona over the other. Solving the coronal heating problem is far from just an academic exercise. It has direct and profound implications for us here on Earth. The superheated corona is the source of the solar wind, the constant stream of charged particles that flows outward through the solar system. The properties of this wind are determined by the conditions in the corona. Furthermore, understanding how energy is released in the corona is key to predicting space weather. The solar storms and coronal mass ejections that, when directed at Earth, can disrupt satellites, knock out power grids, and pose radiation hazards to astronauts. Missions like NASA's Parker Solar Probe, which is flying closer to the Sun than any spacecraft before it, are gathering crucial data right now, diving through the corona itself to directly measure the particles and magnetic fields. Each new measurement brings us closer to unraveling this beautiful paradox, reminding us that even our nearest star still holds profound secrets, challenging our models and pushing the boundaries of our understanding of plasma physics and stellar behavior. After grappling with the solar mystery of a corona hotter than the Sun's surface, our journey into cosmic weirdness takes a turn toward something that sounds like it belongs in an interstellar distillery. It turns out that the universe is not just a vacuum, it's also a surprisingly well-stocked bar. Astronomers have discovered enormous clouds of alcohol drifting in the space between the stars. One of the most famous is a vast molecular cloud near the center of our own Milky Way, known as Sagittarius B2. Within this cosmic cocktail, scientists have identified a particularly fascinating ingredient, vinyl alcohol. Now, this isn't the kind of alcohol you'd find in a drink. It's a simple organic molecule that serves as a direct precursor to more complex amino acids and other compounds essential for life as we know it. The scale of this discovery is almost incomprehensible. This single cloud contains enough vinyl alcohol to create a truly astronomical number of what you might think of as simple plastic molecules, but its significance is far grander than its sheer size. The very existence of these organic clouds challenges a long-held assumption about the origins of life's building blocks. For decades, the prevailing theory was that the complex molecules necessary for life were primarily forged on the surfaces of planets, in the rich chemical soups of early oceans and atmospheres. The discovery of molecules like vinyl alcohol in the cold, dark, and seemingly empty interstellar medium tells a different story. It reveals that the fundamental ingredients for life are not just planetary phenomena, they are cosmic ones. These molecules are formed in the extreme environments of space, on the surfaces of tiny dust grains that are bathed in starlight and cosmic radiation. The process is slow and delicate, with atoms and simple molecules sticking to these cosmic specks of dust and over millions of years, linking together through chemical reactions to form more complex structures. This means that the raw materials for biology are being manufactured on an industrial scale throughout the galaxy, long before planets even form. This has profound implications for the possibility of life elsewhere in the universe. If the basic building blocks are so widespread, literally scattered like seeds across the cosmos, then the emergence of life might be a much more common process than we ever imagined. When a new star and its planetary system condense from a molecular cloud like Sagittarius B2, these pre-made organic molecules are incorporated into the fabric of every comet, asteroid, and planet that forms. The early Earth was almost certainly bombarded by comets and asteroids that were rich in these complex organics, effectively seeding our young world with the chemical starter kit for life. The alcohol clouds in space suggest that this seeding is not a rare event unique to our solar system, but a standard part of planetary formation. The universe, it seems, is pre-biologically primed with the potential for life woven into the very fabric of its star-forming regions. Yet, the presence of these molecules also presents a fascinating puzzle. The interstellar medium is a harsh environment with intense ultraviolet radiation from nearby stars that should, in theory, tear complex molecules apart. So how do they survive and even thrive? The answer lies in the dense, dark cores of these molecular clouds. These regions act as cosmic shields, so thick with gas and dust that they block the destructive radiation, creating a safe haven where chemistry can proceed undisturbed. Within these stellar nurseries, gravity eventually takes over, collapsing the cloud to form new stars and planets, all infused with this rich organic material. So, the next time you look up at the night sky, consider that within the darkness between the stars lies not just emptiness, but a reservoir of potential, a cosmic chemistry set that has been mixing the ingredients for life for billions of years. These clouds of alcohol are more than just a curious fact. They are a testament to a universe that seems inherently predisposed to creating the conditions for biology, suggesting that we are not isolated accidents, but part of a grand, interconnected chemical tapestry that spans the galaxy. Just when we thought the universe couldn't present us with a more profound paradox than a sun with a hot atmosphere, we encounter a world that defies our most fundamental understanding of time itself. On Earth, our calendar is a comfortable, familiar rhythm, 365 days to complete a journey around the sun, and each of those days defined by a single, graceful spin on our axis. It seems like a universal standard, a cosmic rule of thumb. But Venus, our so-called sister planet, gleefully shatters this assumption. Here is a fact that sounds like a riddle. A day on Venus is longer than a year on Venus. To unpack this mind-bending reality, we need to clarify two distinct celestial motions. A year on any planet is the time it takes to complete one full orbit around the sun. A day is the time it takes for the planet to rotate once on its own axis. For Earth, and indeed for most planets, the day is much, much shorter than the year. But Venus operates on a different clock entirely, a clock that seems to be running in reverse and at an almost imperceptible crawl. The reason for this temporal weirdness lies in Venus's rotation. It spins on its axis incredibly slowly. While Earth completes a spin in just 24 hours, Venus takes a staggering 243 Earth days to rotate just once. To make this even stranger, it spins in the opposite direction to almost every other planet in the solar system, a motion known as retrograde rotation. Imagine looking down on the solar system from above the Sun's North Pole. You would see most planets, including Earth, spinning counterclockwise. Venus, however, spins clockwise. This means that on Venus, the Sun would rise in the west and set in the east. Now consider its orbit. Because Venus is closer to the Sun than we are, its year, the time to complete one orbit, is significantly shorter than ours, lasting only about 225 Earth days. So when you do the math, the time for one rotation, 243 days, is indeed longer than the time for one orbit, 225 days. A Venusian day officially outlasts a Venusian year, but the story doesn't end there. From the perspective of someone standing on the surface of Venus, which of course is an impossible and fatal scenario, the definition of a solar day, the time from one noon to the next, is even more complex. Because the planet is slowly rotating backwards as it moves forward in its orbit, the combined motion means the sun would appear to take a very long path across the sky. The result, from one sunrise to the next on Venus, would actually be about 117 Earth days. So, while the planet's sidereal day, its rotation relative to the distant stars, is 243 Earth days, the solar day that would dictate the cycle of light and dark is about half that, but still longer than its year. This combination of a slow, backward spin and a relatively fast orbit creates a calendar that is utterly alien to our Earth-bound experience. The question that naturally follows is why? What catastrophic event in the early solar system could have caused Venus to spin so slowly and in the wrong direction? The leading hypothesis points to a violent beginning. Many planetary scientists believe that in its youth, Venus was likely hit by a massive planetary body, a colossal impact that was so powerful it essentially stopped the planet's original rotation and sent it spinning slowly in the opposite direction. Think of it like striking a spinning top with a hammer. The top might wobble, slow down, and even reverse its spin. This titanic collision could have reset Venus's rotational destiny. Another, more gradual theory suggests that the intense gravitational tides from the Sun, combined with the thick, crushing atmosphere, created a friction that has, over billions of years, braked the planet's rotation to its current sluggish pace. The truth may be a combination of both a primordial impact setting the stage and atmospheric tides fine-tuning the slow, retrograde spin we observe today. This bizarre temporal dynamic has a cascading effect on the planet's environment. The extremely slow rotation means that each hemisphere is baked in sunlight for months on end, contributing to the runaway greenhouse effect that makes the surface hot enough to melt lead. It also means that Venus does not have a meaningful magnetic field generated by a molten core, as the slow spin fails to drive the internal dynamo effect that planets like Earth and Jupiter possess. This lack of a protective magnetic shield leaves Venus exposed to the full force of the solar wind, which over eons has stripped away much of its water. The long day and short year are not just abstract curiosities. They are fundamental factors that shaped Venus into the hellish world it is today. A stark reminder that the basic mechanics of a planet's spin and orbit are directly linked to its ultimate climate and habitability. Venus stands as a cosmic lesson in how small differences in initial conditions, a bump here, a tug there, can lead to dramatically different futures, turning a world of similar size and composition to our own into a place where time itself has been twisted into a paradox. This bizarre relationship with time on Venus shows how a planet's most basic motions can shape its destiny. But if we travel outward to the cold, dark reaches of the solar system, we find a world that defies another fundamental expectation: the idea that a planet's temperature is governed solely by its distance from the Sun. Neptune, the outermost true planet in our system, is a case study in celestial self-sufficiency. It orbits an astounding 2.8 billion miles from the Sun, about 30 times farther out than Earth. At that incredible distance, sunlight is feeble, a mere flicker of its strength here. The amount of solar energy reaching Neptune is about 1/900th of what we receive. You would logically expect this ice giant to be a profoundly cold, frozen, and inert world. Its internal processes long since slowed to a standstill by the deep chill of space. But Neptune is anything but inert. In a stunning revelation, measurements from the Voyager 2 spacecraft showed that Neptune radiates about 2.6 times more energy out into space than it absorbs from the Sun. This means Neptune has a powerful, internal heat source of its own, glowing with a fierce energy that has nothing to do with the distant star it orbits. So, where does this immense internal heat come from? The answer lies in the planet's violent birth and its ongoing, slow-motion collapse. Unlike the rocky terrestrial planets, which are largely solid, Neptune is a gas giant, or more accurately, an ice giant composed primarily of hydrogen, helium, and slushy ices like water, ammonia, and methane. When such a massive planet forms, it does so through the gravitational accumulation of countless planetesimals. As this material crashes together under immense gravity, a tremendous amount of energy is released in the form of heat. This is known as accretion heat, the primordial warmth of creation. For a smaller world like Earth, this initial heat was largely radiated away into space eons ago, though we still feel a remnant of it through volcanic activity and the motion of tectonic plates. But for a planet as massive as Neptune, with over 17 times the mass of Earth, the story is different. Its sheer size makes it a superb insulator. The planet is so massive that the heat generated during its formation, over 4.5 billion years ago, has simply not had enough time to escape. It is still slowly cooling down, and that residual formation heat is one part of the puzzle. The other, and perhaps more significant, process is something called Kelvin-Helmholtz contraction. This is a gradual, ongoing gravitational compression. Imagine Neptune as a gigantic ball of gas and ice. Its own immense gravity is constantly pulling all of its material inward, trying to compress the entire planet into a smaller, denser state. As the planet very slowly contracts under its own weight, the gravitational potential energy of its outer layers is converted into thermal energy, heating the interior. It's a bit like the way a bicycle pump gets warm when you compress the air inside it, but on a planetary scale and over billions of years. This mechanism is thought to be the primary driver of Neptune's internal heat flow today. This internal furnace has profound consequences for the planet's appearance and weather. While the internal heat of a planet like Jupiter also drives its famous storms, the effect on Neptune is even more dramatic because the incoming solar energy is so weak. The heat welling up from Neptune's depths creates tremendous temperature differences between the warmer interior and the frigid cloud tops, powering the most violent winds in the solar system, which can rip across the planet at speeds exceeding 1,200 miles per hour. This internal energy is the engine that drives a dynamic atmosphere where sunlight is little more than a faint suggestion. The mystery deepens when we compare Neptune to its near twin, Uranus. Both planets are similar in size, mass, and composition, and both reside in the outer solar system. Yet Uranus emits barely any excess heat at all. Its energy budget is almost perfectly in balance with the tiny amount of sunlight it receives. This presents a fascinating puzzle for planetary scientists. Why is Neptune so energetically active while Uranus is so quiescent? The leading theory points to a cataclysmic event in Uranus's past. Many scientists believe that Uranus was struck by an Earth-sized object early in its history, an impact so colossal that it knocked the planet onto its side, giving it its extreme 98-degree axial tilt. This impact may have been so violent that it effectively disrupted the planet's core, scattering the hotter internal material and causing much of its primordial heat to escape rapidly into space. Without a well-structured hot core to drive convection, Uranus's internal engine may have stalled. Neptune, on the other hand, might have avoided such a disruptive collision, allowing it to retain its heat and maintain the slow, steady contraction that powers its turbulent atmosphere to this day. This stark difference between the two ice giants shows that even in the cold, distant reaches of our solar system, the history of planetary formation is written in the language of heat, a thermal fingerprint that reveals the violent and unique childhood of each world. Of all the ambitious tools humanity has placed in the heavens, few have captured our collective imagination like the Hubble Space Telescope. Launched with immense promise in 1990, it was designed to be our ultimate eye on the universe, a pristine observatory orbiting high above the distorting effects of Earth's atmosphere. poised to see farther and clearer than ever before. The anticipation in the astronomical community was palpable. This was going to revolutionize our view of the cosmos, but just weeks after its deployment, that promise shattered into $1 billion worth of disappointment. The first images beamed back to Earth were not the crystal-clear vistas of distant galaxies everyone had expected. They were blurry, hazy, and utterly useless for cutting-edge science. A sinking feeling spread through NASA. Something was catastrophically wrong with Hubble's vision. The initial diagnosis was a flaw in the telescope's focusing system, but the terrifying truth soon emerged. The problem was far more fundamental. Hubble's primary mirror, the very heart of the observatory, polished to near perfection over years with painstaking precision, had a fatal flaw. It was suffering from a condition called spherical aberration. Essentially, the mirror was too flat at its edges by a barely perceptible amount, just 1/50th the width of a human hair. But in the realm of optics, where precision is measured in wavelengths of light, that microscopic error was a cosmic-scale disaster. The cause of this error was a stunning failure in the mirror's manufacturing process. The company grinding the mirror had used a device called a null corrector, a special instrument designed to guide the polishing by providing a perfect reference wave front. Unbeknownst to the engineers, a tiny reflective cap on one of the corrector's lenses had been installed slightly incorrectly, a mistake of a mere millimeter. This minuscule misalignment meant the null corrector itself was flawed, and it guided the polishing machines to create a mirror that was, according to its own faulty reference, perfect. But in reality, it was misshapen. The most heartbreaking aspect was that a simple, traditional test using a simple metering rod had actually revealed the error during construction, but its results were dismissed as being less accurate than the supposedly superior null corrector. It was a cascade of human error, a tale of over-reliance on sophisticated technology, and the dismissal of a simpler, correct warning. The result was that when starlight hit Hubble's primary mirror, the light rays reflecting from the edge of the mirror focused to a slightly different point than the light rays from the center. Instead of all the light converging into a single, sharp point, it created a fuzzy halo, rendering the telescope's keen vision hopelessly blurred. The public and media reaction was brutal. Hubble was lampooned as a national joke, a symbol of government waste and engineering incompetence. Late-night talk show hosts had a field day, and editorial cartoons depicted the telescope as a pair of broken glasses. For NASA, still reeling from the Challenger disaster just 4 years earlier, it was a devastating blow to its reputation and morale. Yet, in the face of this humiliation, a remarkable resolve took hold. Scientists and engineers refused to give up on their $2.4 billion observatory. Almost immediately, teams began working on an audacious fix. Since they couldn't bring the faulty mirror back to Earth, they would have to bring the correction to space. The solution was conceived with brilliant elegance. If the primary mirror was flawed, they would design a set of corrective optics, essentially a pair of sophisticated glasses that would precisely counteract the error. This device, called the Corrective Optics Space Telescope Axial Replacement, or COSTAR, would be installed by astronauts on an already planned servicing mission. The first Hubble servicing mission, STS-61, launched in December 1993, became one of the most tense and critically important spacewalks in history. Over the course of 5 grueling days, the crew of the Space Shuttle Endeavour performed a series of complex extravehicular activities, swapping out instruments and, in a nerve-wracking procedure, installing the COSTAR unit. The world watched, holding its breath. When the first new images were transmitted, the effect was instantaneous and breathtaking. The blur was gone. The universe snapped into razor-sharp focus. Galaxies that were once smudges of light now revealed intricate spiral arms and brilliant cores. Nebulae showed ethereal tendrils of gas and dust in stunning detail. The fix was a complete and total success. Hubble was not just repaired, it was reborn, finally capable of delivering on its original revolutionary promise. This turnaround from colossal failure to legendary success is one of NASA's greatest triumphs. It transformed Hubble's public image from a punchline into a beloved icon. More importantly, it demonstrated a profound truth about exploration. The capacity to recover from failure is as important as the ambition to succeed. The CoStar fix paved the way for 4 more servicing missions that upgraded Hubble's capabilities, allowing it to peer ever deeper into the universe. The telescope that began its life as a symbol of embarrassment went on to rewrite astronomy textbooks, confirming the age of the universe, providing evidence for dark energy, and delivering the iconic Hubble Deep Field image that revealed thousands of galaxies in a patch of sky once thought to be empty. The story of Hubble's blurred vision and its heroic fix is a testament to human ingenuity, perseverance, and the refusal to accept defeat, proving that even our greatest mistakes in the pursuit of knowledge can be corrected, often leading to achievements far beyond our initial dreams. The universe's capacity for wonder seems limitless, from the internal heat of distant planets to the triumphant repair of a space telescope. But if we venture to the very edges of observable space and time, we find a discovery that challenges our understanding of cosmic beginnings, a find that revolves around the most essential ingredient for life: water. Imagine a single cloud in the depths of space, so immense and so saturated that it contains 140 trillion times the amount of water in all of Earth's oceans combined. This isn't a science fiction concept. It is the reality of a celestial reservoir discovered surrounding a voracious supermassive black hole known as a quasar, located an almost inconceivable 12 billion light-years from Earth. To grasp that distance is to look back in time to when the universe was in its relative infancy, a mere 1.6 billion years old. The existence of such a vast quantity of water at this early epoch forces a dramatic rethink of how quickly the fundamental building blocks of our cosmos assembled themselves. This monumental discovery was made using an array of powerful radio telescopes, including the submillimeter array in Hawaii and the Plateau de Bure interferometer in France. The focal point of their investigation was this incredibly luminous quasar, officially named APM 08279+5255. Quasars are the intensely bright cores of distant galaxies, powered by supermassive black holes that are actively feeding on surrounding gas and dust. As this material spirals into the black hole's gravitational grip, it forms a searingly hot accretion disk that blazes with energy across the electromagnetic spectrum. It was in the environment surrounding this cosmic engine that astronomers detected the unique spectral signature of water vapor. Water molecules in space can emit radiation at specific microwave wavelengths, and by measuring the intensity and redshift of this signal, scientists could not only confirm the water's presence but also calculate the staggering scale of the cloud and its mind-boggling distance. The implications of finding this much water so early in the universe's history are profound. We often think of the early cosmos as a relatively simple elemental place, dominated by hydrogen and helium forged in the Big Bang. The creation of heavier elements like oxygen, which is a key component of water, required the nuclear furnaces of several generations of stars. These stars would have had to form, live out their lives, and then explode as supernova to seed their surroundings with oxygen, which could then later combine with hydrogen to form water molecules. The presence of a water cloud 12 billion light-years away means that this entire cycle of star birth, death, and molecule formation had already occurred on a colossal scale within the first 1.5 billion years of the universe's existence. This suggests that the early universe was a far more chemically mature and dynamic place than previously assumed, with intense periods of star formation creating the raw materials for water and other molecules with astonishing speed. But why is this water cloud located around a quasar? The environment provides the answer. The process is a delicate cosmic dance between destruction and creation. The immense gravitational power of the black hole does more than just tear matter apart. It also creates the perfect conditions for chemistry. The vast torus of gas and dust swirling around the quasar is both incredibly dense and bathed in the powerful radiation pouring from the accretion disk. This radiation provides the energy needed to drive chemical reactions on the surfaces of dust grains, allowing oxygen and hydrogen atoms to meet and bond into water molecules. Furthermore, the sheer density of the cloud shields these newly formed molecules from being blasted apart by the very radiation that helped create them. The quasar, a beacon of destructive power, inadvertently acts as a colossal catalyst and protector for one of the most crucial molecules in the universe. This discovery does more than just set a record for the largest swimming pool in the cosmos. It fundamentally reshapes our perspective on the abundance of water throughout the universe. If such vast reserves could form so quickly and in such an unlikely environment, then water is likely a common feature of planetary systems across the galaxy and beyond. The water that fills our oceans and flows through our veins may have its origins in processes that began billions of years ago around the hearts of other galaxies. The vapor cloud around APM 08279 plus 5255 stands as a testament to a universe that is not only hospitable to the ingredients of life, but seems almost eager to manufacture them on an unimaginable scale, even in its wildest and most energetic corners. It suggests that the story of water, and perhaps the story of life itself, is woven into the very fabric of cosmic evolution from the very beginning. While our most distant spacecraft carry the story of our world etched in gold, our next fact reminds us that even the grandest cosmic journeys are subject to the universe's most fundamental laws. Consider for a moment the sheer velocity of the Voyager probes, the fastest human-made objects ever to leave our solar system, racing away from the Sun at over 38,000 miles per hour. Yet, for all their incredible speed, their interstellar travel time to even the nearest star is measured not in years or decades, but in tens of thousands of years. This staggering timescale presents a profound challenge for any mission intended to reach another star within a human lifetime, a challenge that has led scientists to dream of a technology that sounds like it belongs in a science fiction novel, a sail propelled not by wind but by light itself. This is the concept of the solar sail, a spacecraft that harnesses the gentle, constant pressure of photons streaming from the Sun. The principle behind a light sail is as elegant as it is counterintuitive. While photons have no mass, they do carry momentum. When light reflects off a surface, it gives that surface a tiny but measurable push. On Earth, this force is imperceptible, utterly drowned out by gravity and atmospheric drag. But in the frictionless vacuum of space, where there is nothing to slow a spacecraft down, this tiny push can accumulate continuously. A solar sail is essentially a gigantic, ultra-thin, and highly reflective mirror. As sunlight particles or photons strike the sail and bounce off, they transfer their momentum to the spacecraft, providing a steady, constant acceleration. Unlike a chemical rocket that fires its engines in a brief, powerful burst and then coasts, a solar sail is always under thrust for as long as it remains in sunlight. There is no fuel to run out of, the sun itself becomes the engine. This method of propulsion offers a revolutionary advantage for long-distance travel. Because it requires no propellant, a solar sailcraft can, in theory, achieve incredibly high speeds over time without the immense weight penalty of carrying fuel. The key factor is the size and lightness of the sail. To catch enough sunlight to generate meaningful thrust, these sails need to be enormous, often spanning thousands of square feet, yet constructed from materials thinner than a human hair. The acceleration starts off incredibly slow, barely perceptible, but with no friction to counter it, the speed builds day after day, week after week, year after year. A solar sail mission starting from Earth could theoretically reach the outer planets in a fraction of the time it took Voyager, and with careful trajectory planning using the gravity of planets for a slingshot effect, it could eventually reach speeds that would make an interstellar voyage conceivable. The promise of this technology moved from theory to reality with missions like Japan's IKROS, which in 2010 successfully demonstrated solar sailing in interplanetary space, and the Planetary Society's Light Sail 2, which has been successfully raising its orbit around Earth using sunlight pressure alone. But the most breathtaking vision for light sails involves taking the concept a step further. Instead of relying solely on our sun, which grows fainter with distance, the Breakthrough Starshot initiative envisions using powerful, ground-based lasers to propel a fleet of tiny, gram-scale probes attached to light sails no bigger than a sailboat sail. This giant laser array would fire a concentrated beam of light at the sails for a few minutes, accelerating the tiny craft to an unprecedented 20% the speed of light. At that velocity, a flyby mission could reach the Alpha Centauri star system, our nearest stellar neighbor, in just about 20 years. The engineering challenges for such a project are, of course, monumental. Building a laser array powerful enough, creating sails that can withstand the immense intensity of the beam without vaporizing, and ensuring the tiny probes can survive the decades-long journey through interstellar space are problems we are only beginning to tackle. Yet, the underlying principle remains sound. Light sailing represents a fundamental shift in how we think about space travel, moving away from the explosive, fuel-limited rocketry of the past toward a more graceful, sustained, and potentially limitless form of propulsion. It is a technology that harnesses a fundamental property of the universe, allowing us to literally ride rays of light on a journey to the stars, turning the gentle pressure of sunshine into the engine for humanity's greatest voyages. After envisioning a future where we sail on beams of light to other stars, we can turn our attention to a world in our own cosmic backyard that already possesses a geography hauntingly similar to our own, yet composed of substances that would be utterly alien to us. Saturn's largest moon, Titan, had long been shrouded in mystery, its surface hidden beneath a thick, orange haze of hydrocarbons. For years, scientists speculated that its cold surface, where temperatures average a bone-chilling -180 degrees Celsius, might host standing bodies of liquid. But it wasn't until the arrival of the Cassini-Huygens mission that this speculation was confirmed in one of the most stunning discoveries of modern planetary science. The Cassini orbiter, using its radar instrument to pierce through the opaque atmosphere, revealed a landscape that was both eerily familiar and profoundly strange. It mapped vast stretches of Titan's surface showing dark, smooth areas that could only be interpreted as lakes and seas. With this revelation, Titan earned a unique distinction. It is the only other world in our solar system, besides Earth, known to have stable liquid resting on its surface. But this is where the familiarity ends. The liquid that fills these lakes is not water. At Titan's frigid temperatures, water is frozen solid, as hard as granite. Instead, the hydrological cycle on this distant moon is based on methane and ethane. These simple hydrocarbons, which are gases here on Earth, exist as liquids on Titan, falling as rain, flowing in rivers, carving out channels, and pooling into lakes and seas that can be hundreds of feet deep. The largest of these, Kraken Mare, located in Titan's North Polar region, is so vast that it is classified as a sea larger than Earth's Caspian Sea. Imagine standing on its shores, not seeing waves of water, but rather waves of liquid natural gas sloshing against a shoreline of water ice as hard as rock. The entire scene would be illuminated by the faint, diffuse glow of a distant sun, appearing as little more than a bright star in a perpetually hazy sky. The existence of this active, methodological cycle makes Titan an incredibly dynamic and Earth-like world in terms of its geological processes. Just as water evaporates from our oceans to form clouds, methane evaporates from Titan's seas, rises into the atmosphere, condenses, and falls back as rain, eroding the landscape and creating features like river deltas and alluvial fans that look strikingly similar to those on our own planet. The Cassini observations even showed changing features on the surface, suggesting that Titan has weather patterns with clouds forming and dissipating and potentially even methane monsoons. This makes Titan a natural laboratory for studying processes that shape terrestrial planets, but under a completely different set of chemical and thermodynamic rules. It's a world that holds up a funhouse mirror to Earth, showing us a version of our own planet where the fundamental liquid of life has been replaced by something entirely different. This radical difference is precisely what makes Titan one of the most compelling targets in the search for life beyond Earth. While the surface is far too cold for life as we know it, which requires liquid water, the possibility of what is called life as we don't know it becomes a tantalizing thought experiment. Could a fundamentally different form of biology arise in the lakes of liquid methane? The chemical reactions would be incredibly slow due to the cold, and methane is a less versatile solvent than water, making the complex chemistry of life far more challenging. However, Titan's environment is rich in complex organic molecules. Its atmosphere is constantly brewing these compounds, which then drift down to the surface like snow. These tholins, as they are known, are the building blocks for more complex chemistry. Some scientists have theorized that a hypothetical life form on Titan could use liquid methane the way we use water, and might even breathe hydrogen gas and consume acetylene for energy. It's a speculative idea, but it forces us to broaden our definition of what life could be and where we might find it. The most intimate glimpse of this strange world came from the Huygens probe, which detached from Cassini and descended through Titan's atmosphere in 2005. As it parachuted down, it sent back the first ever images from the surface of an outer solar system moon. The pictures revealed a landscape of rounded ice pebbles, likely shaped by the flow of liquid methane, in a riverbed or lakebed that was dry at the time. The data confirmed the presence of methane in the soil and a methane humidity in the air, painting a picture of a world that is periodically wetted by rainfall. The success of Huygens gave us a ground-level perspective on this alien hydrology, transforming Titan from a blurred orange ball into a world with a tangible, rugged, and strangely beautiful landscape. Future missions are already being planned to explore Titan's lakes more directly. NASA's Dragonfly mission, scheduled to launch in the late 2020s, will send a drone-like rotorcraft to fly through Titan's thick atmosphere, which makes flight easier than on Earth, and land at multiple sites to sample the surface composition. Dragonfly will explore the sand dunes and dry lakebeds of Titan, searching for complex organic molecules and studying the moon's habitability. The prospect of a robotic drone flying over the icy terrain and perhaps even near the hydrocarbon seas is a testament to our enduring fascination with this world. Titan stands as a profound reminder that habitability may not be a single, narrow set of conditions, but a spectrum of possibilities. It challenges our Earth-centric view of life and presents us with a second example of an active, liquid-based world, one that is both a frozen relic from the early solar system and a potentially fertile ground for chemistries we are only beginning to imagine. While our gaze has been fixed on the far reaches of the solar system, a slow but monumental change is unfolding much closer to home, a subtle dance of gravity that is gradually altering the very fabric of our sky. The moon, our constant celestial companion, is in the process of leaving us. It is not a sudden departure, but a gradual, inexorable retreat, drifting away from Earth at a rate of roughly 3.8 centimeters each year. This fact, which might seem like a trivial distance on a human timescale, is one of the most precisely measured phenomena in astronomy, and its implications stretch billions of years into the future. The story of how we know this with such certainty is a testament to human ingenuity, and it begins with a series of mirrors placed on the lunar surface by the Apollo astronauts. The key to this discovery lies in a technique called lunar laser ranging. The Apollo 11, 14, and 15 missions each left behind small arrays of corner cube retroreflectors on the Moon. These are not ordinary mirrors. They are designed with a specific geometric property that ensures any light beam hitting them is reflected directly back to its source, regardless of the angle of incidence. Here on Earth, powerful lasers at observatories like the one at the Apache Point Observatory in New Mexico are fired in precise pulses toward these reflectors. The journey is staggering. The laser light travels nearly 400,000 kilometers to the Moon, bounces off the reflector, and makes the return trip. By measuring the exact time it takes for that pulse of light to complete its round trip, a journey of about 2.5 seconds, scientists can calculate the distance to the Moon with an accuracy of a few millimeters. It is, in essence, the most precise tape measure ever devised. This incredibly precise measurement, repeated over decades, has revealed the Moon's slow but steady recession. The driving force behind this cosmic retreat is the same phenomenon that gives us ocean tides: gravity. The Moon's gravitational pull creates a bulge in Earth's oceans and to a lesser extent in its solid body. However, because Earth rotates on its axis much faster than the Moon orbits around us, our planet's spin drags this tidal bulge slightly ahead of the direct line between Earth's center and the Moon. This leading bulge, in turn, exerts its own gravitational tug on the Moon. This pull is subtle, but it has a profound effect. It transfers a tiny amount of Earth's rotational energy to the Moon, giving it a slight push that causes it to spiral into a slightly higher and therefore slower orbit. In simple terms, Earth's rotation is literally pushing the Moon away. This exchange of energy is a two-way street, and it has consequences for our planet as well. As the Moon gains orbital energy and moves away, Earth loses rotational energy. This means our planet's spin is gradually slowing down, making our days longer. The effect is minuscule. Each century, the day lengthens by about 1.7 milliseconds, but over geological time, it adds up. Evidence from fossilized growth rings in ancient corals shows that 400 million years ago, an Earth day was only about 22 hours long, and a year contained nearly 400 days. The Moon was also significantly closer, appearing larger in the sky and causing much more dramatic tides. This process will continue. As the Moon continues to recede, Earth's days will grow ever longer. In the distant future, a day on Earth might eventually become as long as a month is today, a state known as tidal locking. What does this mean for the ultimate fate of the Earth-Moon system? The recession will not continue forever. Eventually, the same process that is driving the Moon away will reach a natural conclusion. Billions of years from now, if the Sun hadn't already expanded into a red giant and engulfed both worlds, Earth's rotation would slow to the point where it becomes tidally locked with the Moon, meaning one side of Earth would permanently face the Moon, just as one side of the Moon always faces us. At that point, the transfer of energy would cease, and the Moon's orbital distance would stabilize. The once familiar monthly cycle of lunar phases would vanish from half the planet, and the ocean tides as we know them would become a thing of the past, fixed in place by this final gravitational embrace. This slow, graceful dance of separation is a reminder that even the most seemingly permanent features of our sky are in a state of constant, dynamic flux, playing out on a timescale that dwarfs human history but is written in the fundamental laws of physics that govern our universe. While the Apollo astronauts' reflectors provided a precise benchmark for measuring the Moon's slow retreat, they are not the only mirrors adorning the lunar surface. There exists another, one that carries with it a tale of Cold War rivalry, technological triumph, and a mystery that stretched for nearly 4 decades. This is the story of the Lunar 1 rover and its French-built laser reflector. a device that was successfully used for a time, then vanished without a trace, only to be miraculously rediscovered, turning a forgotten Soviet relic into a crucial tool for modern science. The Lunokhod 1 mission was a landmark achievement in robotic exploration. Launched by the Soviet Union in 1970, it was the first remote-controlled rover to successfully operate on another world. This 8-wheeled, bathtub-shaped vehicle, trundling across the volcanic plains of Mare Imbrium, was a marvel of engineering for its time. Controlled with a significant time delay from Earth, its drivers navigated the treacherous terrain for nearly a year, far exceeding its planned 3-month mission. Among its suite of scientific instruments was a compact, French-built array of corner-cube retroreflectors, similar in function to the larger American versions deployed by the Apollo crews. For a time, scientists successfully bounced laser beams off this Soviet reflector, adding another date to point to the growing understanding of the Earth-Moon system. But in September 1971, after 11 months of operation, Lunokhod 1 fell silent, its final location not precisely known. As the years turned into decades, the exact spot where the rover ended its journey was lost, and with it, the ability to use its reflector. It became a ghost on the Moon, a piece of functional technology rendered invisible by the vast, empty expanse of the lunar surface. The mystery of Lunokhod 1's whereabouts persisted until 2010, when a team of physicists from the University of California, San Diego, had a brilliant idea. They petitioned the team operating NAS, a Lunar Reconnaissance Orbiter, or LRO, which was meticulously mapping the Moon's surface in unprecedented detail. By examining old archival data and analyzing the rover's last known transmissions, they narrowed down a search area. The powerful cameras aboard LRO were then tasked with scanning this region of Mare Imbrium. The hunt was a success. There, in the high-resolution images, was the Lunokhod 1 rover, along with the tracks it had made in the lunar soil 4 decades earlier. They had found the needle in the haystack, but the real challenge was still to come. Could they actually hit the tiny reflector with a laser beam from Earth? The team at the Apache Point Observatory in New Mexico aimed their laser at the newly discovered coordinates. The probability of success was considered low. The reflector was small, and after 40 years, it might have been covered by dust or become misaligned. Yet, on their first attempt, they received a strong, clear signal back. The lost reflector had been awakened. Not only was it functional, but to the scientists' astonishment, it was returning a signal even brighter than those from the larger Apollo arrays. The reason for this unexpected performance remains a topic of investigation. One theory suggests that the rover's design may have left the reflector at a slight angle, and over time, a natural accumulation of fine lunar dust on its surface may have actually acted to optimize its angle relative to Earth, making it a more efficient mirror. It was a fortunate twist of fate, a case of environmental wear inadvertently enhancing a decades-old instrument. The rediscovery of Lunokhod 1's reflector was far more than a historical curiosity. It provided a major scientific windfall. Having a functional reflector at a significantly different lunar latitude than the Apollo sites greatly improves the precision of lunar laser ranging experiments. It's akin to measuring the wobble of a spinning top. If you only take measurements from one point on the top, your data is limited. But if you have multiple points of reference, you can calculate the wobble with far greater accuracy. The data from Lunokhod 1 allows scientists to study the Moon's libration, its subtle rocking back and forth as it orbits, with much finer detail. This, in turn, provides incredibly precise information about the Moon's internal structure, helping to determine the size and state of its core, whether it's partially molten or solid. Furthermore, by comparing the signals from the different reflectors, physicists can conduct exquisitely sensitive tests of fundamental theories like Einstein's theory of general relativity, checking for any tiny deviations in the gravitational constant over time. A mission that had been consigned to the history books was suddenly reborn as a cutting-edge tool for probing the deepest secrets of gravity and celestial mechanics, a poignant bridge between the space race of the past and the scientific inquiries of the present. And so we arrive at a paradox that seems to defy all logic, a world of extremes where the possibility of ice exists right next to unimaginable heat. Mercury, the innermost planet, is a scorched and airless world. By day, with the sun appearing 3 times larger in its sky than from Earth, surface temperatures soar to a blistering 430 degrees Celsius, hot enough to melt lead. It is, by any measure, the solar system's ultimate furnace. Yet, hidden in the perpetual darkness of its polar regions, lies a secret that astronomers only confirmed in the 21st century: vast deposits of water ice. This discovery was so counterintuitive that for decades it was dismissed as an impossibility. How could a planet so close to the Sun, a world without a protective atmosphere to shield it, possibly harbor frozen water? The answer lies not in the planet's surface, but in the precise geometry of its rotation and the cosmic delivery service that brought the water there in the first place. The key to this frozen enigma is Mercury's unique axial tilt, or more accurately, its lack of one. Unlike Earth, which is tilted on its axis, giving us seasons and ensuring that every part of the planet receives some sunlight throughout the year, Mercury's axis is almost perfectly perpendicular to its orbit. This means that the floors of deep craters at its poles never, ever see the light of the sun. They are cast in an eternal, profound shadow, a permanent night that has lasted for billions of years. Within these sunless basins, temperatures can plunge to a bone-chilling -170 degrees Celsius, colder than even the ice-rich surface of Jupiter's moon Europa. These craters act as natural deep freezes, creating microscopic cold traps where any volatile substance that finds its way inside is captured forever. The boundary between a crater floor in permanent shadow and its sunlit rim is one of the most extreme temperature gradients in the entire solar system, a stark dividing line between inferno and icebox. This revelation came primarily from NASA, a messenger spacecraft which orbited Mercury from 2011 to 2015. Messenger carried several instruments that, when their data was combined, provided irrefutable proof. Neutron spectrometers measured a signature consistent with hydrogen-rich deposits, which on a world like Mercury almost certainly means water ice. But the most visually striking evidence came from laser altimeters. By mapping the topography of the polar regions in exquisite detail and comparing it with radar reflectivity data collected earlier from Earth, scientists could see that the areas with incredibly bright radar returns, a classic signature of water ice, correlated perfectly with the locations of these permanently shadowed craters. The ice isn't just a thin frost. In some craters, it's thought to be several meters thick, potentially containing billions of tons of water. So, if the ice can't form on Mercury itself, where did it come from? The planet is far too hot and its gravity too weak to have held onto water from its formation. The water is an import delivered over billions of years by comets and water-rich asteroids. These icy wanderers from the outer solar system occasionally have their orbits perturbed, sending them on a death dive toward the Sun. When they collide with Mercury, the immense energy of the impact vaporizes most of their water, which then escapes into space. However, a small fraction of this water molecules can bounce across the surface. In the airless environment, a water molecule can travel a significant distance until it happens to drift into one of these polar cold traps. Once inside the shadowed confines of a crater, the molecule loses its kinetic energy and adheres to the cold soil, joining a slowly accumulating layer of ice. Over astronomical timescales, countless cometary impacts have seeded the poles with enough water to build up the substantial deposits we see today. It's a continuous, slow-motion drizzle of cosmic ice, with the polar craters acting as perfect catchment basins. The presence of this ice has profound implications not just for our understanding of Mercury, but for the entire inner solar system. It demonstrates that water, that essential ingredient for life as we know it, is surprisingly mobile. It can be transported across vast interstellar distances and deposited even in the most seemingly hostile environments. This process likely occurred on the Moon as well, which also has ice in its polar craters and perhaps even on other airless bodies. For future exploration, Mercury's ice represents a potential resource. While establishing a human presence on Mercury is a distant dream due to the extreme temperatures and solar radiation, the existence of water ice means that a future robotic mission could, in theory, use it to produce breathable air and rocket fuel, turning a dead world into a potential stepping stone for deeper voyages into the solar system. The discovery of ice on Mercury transforms it from a simple, scorched relic into a dynamic world with a complex history of cosmic bombardment and volatile trapping, a testament to the interconnected nature of our planetary system and the unexpected ways water can find a home in the most unlikely of places. While our journey has taken us to worlds of ice and fire and to the far reaches of the solar system, one of the most profound and poignant chapters in the story of space exploration unfolded much closer to home with a being who never asked to be a hero. Before a human had ever felt the crushing grip of gravity at launch or the surreal weightlessness of orbit, we had to know if a living creature could even survive the experience. The answer to that question came in the form of a small, mixed-breed dog plucked from the streets of Moscow, a dog the world would come to know as Laika. Her mission aboard Sputnik 2 in 1957 marked a pivotal milestone, a grim but necessary step that paved the way for human spaceflight. Yet it is a story forever shadowed by the ethical questions it raises about the price of progress. Laika was not a highly trained purebred. She was a stray, a 3-year-old husky mix found wandering the Soviet capital. Soviet scientists believed that a stray dog would already be equipped to endure the extreme hardships of cold and hunger, making them ideal candidates for the rigors of spaceflight. Along with several other candidates, Laika underwent a brutal training regimen designed to prepare her for the mission. She was confined in progressively smaller cages for weeks on end to acclimate her to the tight quarters of the spacecraft's cabin. She was placed in centrifuges that simulated the high G-forces of launch and subjected to loud, jarring noises that mimicked the roar of a rocket engine. Through it all, her calm demeanor and resilience stood out, and she was chosen for the one-way mission. The spacecraft Sputnik 2 was a hastily constructed cone-shaped module rushed to launch to celebrate the 40th anniversary of the Bolshevik Revolution. It was equipped with a life support system, an oxygen generator, a device to absorb carbon dioxide, and a simple feeding apparatus that would provide a gelatinous, nutritious food. On November 3, 1957, Laika was sealed inside her tiny, pressurized cabin. There was scarcely room for her to move. She could only stand, sit, or lie down. When Sputnik 2 roared into the sky, sensors transmitted data back to Earth, showing that Laika's heartbeat soared to triple its normal rate under the stress of launch. Once in orbit, as weightlessness set in, her pulse gradually decreased, but it still remained well above her resting rate, indicating she was under significant, sustained stress. For a few hours, she became the most famous dog on the planet, a symbol of Soviet technological prowess and the living proof that a mammal could survive in orbit. But the triumphant narrative presented to the world concealed a dark and somber truth. The technology to return a spacecraft from orbit safely did not yet exist. Sputnik 2 was never designed to be recovered. From the very beginning, Laika's mission was a suicide trip. For decades, the official Soviet account of Laika's fate was that she lived for several days, after which she was humanely euthanized with a poisoned portion of food before her oxygen supply could run out. It was a story that, while tragic, offered a veneer of dignity, However, the real story, which did not emerge until many years later, was far more distressing. In 2002, Dmitry Malyshenkov, a scientist who had worked on the Sputnik 2 mission, revealed that Laika had survived only a few hours in orbit. The hastily built spacecraft had inadequate thermal protection. As it passed in and out of sunlight, the cabin began to overheat dramatically. The temperature quickly rose to over 40 degrees Celsius. The sensors showed that after the third orbit, her life signs ceased. Laika had died from overheating and panic, a lonely and terrifying death in the void. The mission provided crucial data, proving that a living organism could withstand launch and weightlessness, but it came at a cost that forced the world to confront the moral dilemmas of scientific ambition. Laika's sacrifice was not in vain. The data from her mission directly informed the design of life support systems for the cosmonauts and astronauts who would follow her. Her story ignited a global debate about the ethics of using animals in research, leading to stricter guidelines and a greater emphasis on animal welfare in later space programs. While other dogs and later primates would fly and be successfully recovered, Laika's name is etched in history as the first, a tiny, innocent creature whose journey began on the cold streets of Moscow, ended 2,000 miles above them, a silent pioneer whose barks were never heard in the stillness of space, but whose legacy echoes in every human mission that has followed. She is a stark reminder that behind the cold, hard data of engineering triumphs are often stories of immense courage and profound sacrifice, a bittersweet chapter in our ascent to the stars. Circling the red planet are two of the most unusual satellites in the entire solar system, cosmic afterthoughts that seem almost too strange to be real. Unlike our own majestic spherical moon, the moons of Mars, Phobos and Deimos are little more than lumpy, cratered rocks, often compared to misshapen potatoes. Their dimensions are a testament to their irregularity. Phobos, the larger of the two, measures only about 27 kilometers across at its widest point, while Deimos is a mere 15 kilometers. They are so small and dark, with surfaces resembling charcoal, that they were nearly impossible to spot with 19th-century telescopes. In fact, their discoverer, Asaph Hall, was on the verge of giving up his search in 1877 when his wife urged him to continue. He found Deimos the next night and Phobos just 6 nights after that. Their names, meaning fear and dread in Greek, were fitting choices for the attendants of the Roman god of war. But these moons are less terrifying warriors and more like two quiet, oddly shaped sentinels keeping a distant watch over their rusty parent planet. The most compelling clue to their origin lies in their very appearance. Their irregular shapes and dark, carbon-rich composition are dead ringers for the asteroids that populate the main belt between Mars and Jupiter. The leading theory suggests that Phobos and Deimos did not form in orbit around Mars, as our moon did around Earth. Instead, they are likely captured asteroids, wandering ancient bodies that ventured too close to the gravitational influence of Mars billions of years ago. The exact mechanism of this capture is a subject of debate. It's notoriously difficult for a planet's gravity to gently slow a passing asteroid enough to pull it into a stable orbit. Usually, the object either crashes into the planet or gains speed and slingshots away. One plausible scenario involves a much more massive, porous asteroid being captured and then breaking apart due to tidal forces, with Phobos and Deimos being the two largest surviving fragments. Another theory points to a giant impact on Mars, similar to the one that created Earth's moon, suggesting these odd moons could be debris from that collision that coalesced into their current forms. Regardless of their precise origin story, their captured status explains their distinct lack of geological activity and their ancient, unevolved surfaces, which are among the oldest and most cratered landscapes we have observed. But the true weirdness of this duo is not just their past, but their future, particularly for the inner moon, Phobos, orbiting incredibly close to Mars, so close that it circles the planet 3 times a day. Phobos is locked in a celestial dance with a fatal conclusion. Detailed measurements have confirmed that this moon is gradually spiraling inward, moving about 2 meters closer to Mars every century. The cause of this slow decay is the same tidal force that is pushing our own moon away from Earth, but with a critical difference. Mars rotates more slowly than the moon Phobos orbits. This means the gravitational tug of Mars creates a tidal bulge on Phobos, but the planet's rotation drags this bulge slightly behind, creating a gravitational break that saps energy from the moon's orbit. Instead of being pushed away, Phobos is being pulled down. In about 50 million years, this inward spiral will bring Phobos within a critical distance known as the Roche limit. This is the point where a planet's gravitational tide becomes stronger than the gravitational force holding a moon together. When Phobos crosses this threshold, the relentless pull of Mars will overcome the relatively weak self-gravity of the small, rubble-pile moon. It will not simply crash into the surface in one piece. Instead, it will be slowly, methodically torn apart. The process will be spectacular. Phobos will fracture into a cascade of rocks and dust spreading out along its orbital path. For a time, Mars will sport a magnificent transient ring system, a pale, rocky halo circling the equator. Gradually, over millions of more years, this ring will destabilize, and the debris will rain down upon the Martian surface in a long, drawn-out meteor shower. This impending destruction makes Phobos a unique natural laboratory for studying orbital dynamics and tidal forces in action. It also presents a poignant cosmic timeline, a reminder that even the most seemingly permanent celestial arrangements are temporary, with their own cycles of capture, decay, and ultimate disintegration playing out over spans of time that dwarf human history. But to truly appreciate the spectacle of a comet, we must first dismantle a common misconception, one beautifully illustrated in the night sky. We often picture a comet as a solitary rock with a long, flowing tail stretching out behind it as it hurtles through space like a speedboat's wake. This intuitive image is only half right, and the full truth is far more dynamic and revealing. A comet doesn't have just one tail, it typically has 2, and they behave according to 2 completely different sets of physical laws. Understanding this duality is the key to reading the story written across the heavens whenever one of these icy visitors graces our sky. The first tail is the one that aligns with our intuition, the dust tail. This is composed of tiny particles of dust and grit, no larger than grains of sand, that are liberated from the comet's nucleus as the sun's heat turns its surface ice directly into gas, a process called sublimation. These dust particles are relatively heavy, at least on a cosmic scale. As the comet speeds along its orbit, this dust is left drifting in its wake, forming a broad, softly glowing, and often curved tail that does indeed trail behind the comet's path. Its gentle curve is a result of the individual dust particles following their own slightly slower orbital trajectories around the sun compared to the comet itself. This tail reflects sunlight, giving it a whitish or yellowish glow, and it's the most photogenic part of the comet, the part that looks most like a celestial brushstroke. The second tail, however, is where the true cosmic weirdness lies. This is the ion tail, also known as the gas tail or plasma tail. It is born from the same process solar heating vaporizing ices, but the fate of these released gases is radically different. The sun doesn't just emit light and heat, it constantly blows out a stream of charged particles known as the solar wind. This wind, moving at speeds of over 1 million miles per hour, bathes the entire solar system. When the neutral gas molecules from the comet's coma are hit by the solar wind and the sun's own ultraviolet radiation, they become ionized, stripped of their electrons, becoming electrically charged. Once charged, these ions are exquisitely sensitive to the magnetic fields carried by the solar wind. They are instantly caught and swept directly away from the sun, much like iron filings aligning with a magnet. This creates a tail that is always pointing radially away from the sun, regardless of the direction the comet is traveling. This leads to the breathtaking and counterintuitive sight that can confuse ground-based observers. When a comet is heading away from the sun after its closest approach, both tails stream out behind it and the illusion holds. But when a comet is diving toward the sun, the situation becomes spectacularly strange. The dust tail will still lag behind the nucleus, but the ion tail will be pointing almost directly ahead of it toward the direction of travel. From our perspective on Earth, it can look as though the comet is rushing backward with a spear-like tail leading the way. This is a perfect real-time demonstration of the solar wind's power. The ion tail is often much straighter and sharper than the diffused dust tail, and it glows with a distinct bluish color. This ethereal light isn't reflected sunlight, it's fluorescence. The ionized molecules, most commonly carbon monoxide ions, get excited by the solar wind and re-emit light at a specific blue wavelength, creating a ghostly, radiant beam that charts the invisible magnetic currents of interplanetary space. Observing these two tails tells astronomers a great deal about the comet's composition and the conditions in the solar system. The dust tail reveals the size and quantity of solid material the comet is shedding. The ion tail, acting as a cosmic windsock, provides a direct readout of the solar wind's speed and intensity. Sometimes this tail can appear to disconnect and then reform. This isn't the tail breaking off, it's a sign that the comet has passed through a region where the sun's magnetic field has suddenly shifted direction, temporarily disrupting the flow of ions before they can realign. So, the next time you see an image of a comet like Neowise or Hale-Bopp, take a moment to look closely. You're not just seeing a streak of light, you're witnessing a complex dance between gravity, radiation, and magnetism, a celestial object being sculpted in real time by the forces of the sun, displaying not one, but two separate stories written across the dark canvas of space. While the silent ballet of comets and the slow drift of our moon speak to the natural rhythms of the cosmos, a far more urgent and human-made drama is unfolding in the space just above our heads. As we've expanded our presence beyond Earth, we've left behind a ghost fleet of our own ambition, a swirling sea of orbital debris that poses one of the most pressing threats to our future in space. This isn't just a few lost screws, it's a cloud of high-speed shrapnel that grows more dangerous with every passing year. Imagine a shell of territory surrounding our planet, from a few hundred to over 20,000 kilometers in altitude, that is now cluttered with the defunct remnants of our technological age. Dead satellites the size of school buses, discarded upper stages of rockets, fragments from explosions, and countless millions of smaller pieces like flecks of paint and bolts, all traveling at velocity exceeding 17,000 miles per hour. At those speeds, even a tiny chip of paint carries the kinetic energy of a bullet, capable of shredding solar panels, cracking windows, or disabling a critical satellite. The genesis of this problem lies in the very nature of how we've used space for the past 6 decades. For a long time, the mindset was one of a limitless frontier. When a satellite reached the end of its life, it was simply abandoned. Rocket stages that delivered payloads to orbit were left to drift. Occasionally, catastrophic events made the problem exponentially worse, such as the 2007 Chinese anti-satellite missile test that deliberately destroyed a weather satellite, creating over 3,000 trackable pieces of debris, or the 2009 accidental collision between an active American communications satellite and a defunct Russian one, which added another 1,000 fragments to the ledger. Each collision doesn't just create 2 pieces of junk, it creates a shotgun blast of new projectiles, each one a potential weapon capable of causing another collision. This is the heart of the nightmare scenario known as the Kessler syndrome, proposed by NASA scientist Donald Kessler in the 1970s. The Kessler syndrome describes a potential tipping point, a cascading chain reaction where the density of debris in a particular orbital band becomes so high that collisions occur spontaneously. One collision creates hundreds of new pieces of debris, each capable of causing another collision, which in turn creates even more debris. The result would be an exponentially growing cloud of shrapnel that could render entire orbital regions, particularly the valuable low Earth orbit where the International Space Station and many Earth observation satellites reside, effectively unusable for generations. It would be like creating an impassable asteroid belt of our own making, trapping us on Earth and severing our access to the vital services that satellites provide, from global communications and weather forecasting to GPS and national security. This isn't a distant sci-fi plot, it's a realistic risk that satellite operators now have to factor into every mission, regularly performing debris avoidance maneuvers to dodge known pieces of trackable junk. Recognizing the severity of this self-created threat, the world's space agencies and a new wave of private companies are shifting from mere tracking to active remediation. The first and most crucial step is prevention. Modern guidelines, though not always legally binding, encourage operators to design satellites with plans for their end of life, such as reserving enough fuel to deorbit them into the atmosphere where they will safely burn up, or moving them to a graveyard orbit far away from active traffic. But prevention alone cannot solve the problem of the debris already up there. This has sparked a global race to develop active debris removal, or DR technologies. The concepts are as ingenious as they are varied. Some proposals involve giant nets that will be deployed to ensnare a defunct satellite like a cosmic fisherman. Others imagine robotic arms that would grapple onto a piece of junk and guide it to a controlled re-entry. One particularly elegant idea is the use of harpoons, which would be fired into a large object, allowing a tugboat spacecraft to then pull it out of orbit. Perhaps the most futuristic concept involves lasers. Rather than blasting debris to smithereens, which would only make the problem worse, the idea is to use ground-based or space-based lasers to gently push on smaller pieces of debris. The laser beam would vaporize a tiny portion of the object's surface, creating a minuscule jet of plasma that would impart just enough force to nudge the debris into a lower orbit, hastening its atmospheric decay. The European Space Agency is leading the way with its Clear Space mission, a partnership with a Swiss startup that plans to launch the first dedicated debris removal spacecraft. Its target is a single, specific object, a payload adapter left in orbit by a Vega rocket launch in 2013. The mission, Clear Space One, will rendezvous with this piece of junk, capture it using a sophisticated four-armed claw, and then perform a controlled deorbit, burning up together with its captured prey. This mission is a critical proof of concept, aiming to demonstrate that we can not only create this mess but also clean it up. The challenge of space junk is a powerful reminder that our actions have consequences beyond our atmosphere. It is a test of our maturity as a spacefaring civilization. Solving it will require unprecedented international cooperation, as debris knows no national borders, and the technology to remove it could also be misused as an anti-satellite weapon. The economic stakes are immense, with trillions of dollars of infrastructure in orbit supporting our modern way of life. But beyond the economics and the technology, it is an ethical imperative. We have a responsibility to be good stewards of the orbital environment, to ensure that the pathways to the stars remain open for future generations of explorers, scientists, and dreamers. The effort to clean up our celestial backyard is a monumental task, but it represents a crucial evolution in our relationship with space, from one of reckless expansion to one of thoughtful, sustainable presence. And as we grapple with the man-made challenge of orbital debris, a far grander and more inevitable cosmic event is unfolding on a scale so vast it defies human comprehension. Our entire galaxy, the Milky Way, with its 400 billion stars, our Sun among them, is on a collision course. The Andromeda Galaxy, our closest major galactic neighbor, is hurtling towards us at an incredible speed of about 250,000 miles per hour. But before you picture a celestial car crash of epic proportions, you need to understand the true nature of this event, which is less about violent impact and more about a slow, majestic, gravitational dance that will reshape the night sky over billions of years. The key to understanding this lies in the sheer, mind-boggling emptiness of space. We look up at a starry night and see a sky filled with points of light, but this is an illusion of perspective. The distances between those stars are almost unimaginably vast. If the Sun were the size of a grapefruit here on Earth, the nearest star, Proxima Centauri, would be another grapefruit located nearly 2,000 miles away. Now scale that up to the galactic level. The Milky Way is a disk 100,000 light-years across, but it's only about 1,000 light-years thick on average. It is effectively an immense collection of tiny, isolated specks separated by oceans of nothingness. So when two such galaxies meet, it's not like two swarms of bees crashing into each other. It's more akin to two vast, ghostly clouds of smoke gently passing through one another. The probability of any two stars from the Milky Way and Andromeda actually colliding is astronomically low, virtually zero. Their individual paths will be bent and altered by gravity, but they will simply glide past one another, their personal space remaining largely undisturbed. This doesn't mean the event will be uneventful. The real action happens not with the stars themselves, but with the immense clouds of gas and dust that populate the interstellar medium. These clouds are far more substantial and will most certainly collide. When they do, the result will be a spectacular, galaxy-wide fireworks display. The collisions will trigger violent shock waves, compressing the gas and dust and igniting a frenzy of new star formation. This stellar baby boom will light up both galaxies, creating brilliant blue clusters of young, hot stars. For a time, the merging galaxies will blaze with the light of billions of new suns, a radiant, if temporary, rebirth. This burst of creation, however, will eventually consume the very fuel that sustains it. After this period of furious stargazing, the galaxies will settle down, having used up much of their remaining gas, and star formation will slowly decline. The entire process is a slow-motion ballet choreographed by gravity, playing out over an almost incomprehensible timescale. The first close pass is predicted to occur about 4 billion years from now. At that point, from the perspective of any life on Earth, assuming our planet is still habitable, the Andromeda Galaxy will begin to dominate the night sky. It will grow from a faint, fuzzy smudge into a magnificent, sprawling band of light. As the galaxies swing past each other, their gravitational pull will warp and distort their familiar spiral shapes, stretching them into long, streaming tails of stars, gas, and dust. This initial encounter will be dramatic, but it won't be the end. The two galaxies, now gravitationally bound, will separate slightly before falling back towards each other for a second and final merger. Over the next 1 to 2 billion years, they will swing around each other again and again, each pass further mingling their stars until they finally coalesce into a single new galaxy. The final product of this cosmic union will likely be an elliptical galaxy, a vast, featureless egg-shaped collection of stars, a far cry from the elegant spiral arms of the original Milky Way and Andromeda. Our solar system will almost certainly survive this entire process, though it will likely be flung into a much larger, more distant orbit within the new galactic core. The night sky from Earth would be utterly transformed, devoid of the familiar Milky Way band, but filled with a dense, brilliant sphere of stars from the combined galaxies. This event, the merger of two great islands of stars, is not a unique catastrophe. It's a standard part of galactic evolution. We see evidence of such mergers throughout the observable universe. The knowledge that our own galaxy has such a dramatic future written in the stars is a humbling reminder of the dynamic, ever-changing nature of the cosmos, where even the largest structures are subject to the slow, irresistible pull of gravity, destined to collide, merge, and be reborn on a timescale that transcends all human conception of time. Leaving behind the familiar pull of Earth's gravity is a profound physical transition, one that comes with a surprising and often unpleasant welcome gift for many who make the journey. While we often picture astronauts as superhuman figures of perfect health and composure, the reality is that about half of them are struck by a temporary but debilitating condition the moment they reach orbit, an ailment known officially as space adaptation syndrome, but more commonly called space sickness. Imagine the disorientation. After the violent shaking and immense G-forces of launch, the rocket engines cut off, and you are suddenly weightless. The straps of your seat no longer hold you down, and every loose object begins to float. For many, this thrilling moment is quickly overshadowed by a wave of nausea, cold sweats, headache, and vertigo that can last for several days. It's the human body's immediate, visceral protest against an environment for which it was never evolutionarily designed. The root cause of this sickness lies in a fundamental sensory conflict deep within our biology, specifically a battle for control between your eyes and your inner ear. Here on Earth, the vestibular system in your inner ear is a brilliantly calibrated instrument for gravity. It contains tiny, fluid-filled canals and microscopic crystals called otoliths that shift with every movement, constantly telling your brain which way is down, how your head is tilted, and whether you are accelerating or decelerating. This system works in perfect harmony with your vision. When you walk, your eyes see the world moving, and your inner ear feels the corresponding motion the signals match. But in the microgravity of space, this partnership falls apart. The otoliths, which rely on gravity to provide their reference, are now floating aimlessly, sending confused and chaotic signals to the brain that essentially report a state of constant, uncontrolled tumbling. Meanwhile, your eyes look around the spacecraft cabin and see a perfectly stable, stationary environment. The brain receives these wildly contradictory reports, the ears screaming that you're in a catastrophic spin, while the eyes insist that everything is perfectly still. This neural dissonance is interpreted by the brain as a hallucination, likely caused by a neurotoxin, and the most primitive survival mechanism kicks in, the vomit reflex, an attempt to expel a perceived poison. The experience of space sickness is highly individual and notoriously difficult to predict. Some veteran pilots who have never experienced a hint of motion sickness in high-performance jets find themselves completely incapacitated in orbit. Others who might get queasy on a boat adapt to weightlessness with ease. There seems to be no correlation with age, gender, or physical fitness. To manage this, astronauts are taught strategies before their flight. They are advised to minimize rapid head movements, especially looking up and down, which can trigger the conflicting signals instantly. During the first critical days, they often focus their gaze on a fixed point in the cabin to give their visual system a stable anchor. Mission planners deliberately schedule a light workload for the initial 48 hours, allowing the crew time to adapt without the pressure of complex tasks. When sickness does strike, medication is available, but many astronauts prefer to avoid it unless absolutely necessary, as the drowsiness that can accompany anti-nausea drugs is itself a handicap when you need to be alert in a dangerous environment. The most fascinating part of this syndrome, however, is not the sickness itself, but the remarkable process of adaptation that follows. The human brain is incredibly plastic. After a period of confusion lasting typically 1 to 3 days, it begins to learn a new rule. In this strange place, ignore the signals from the inner ear. The brain starts to rely almost exclusively on visual cues to determine orientation and movement. It's a conscious recalibration of the body's entire balance system. Astronauts often describe a distinct click moment when their perception suddenly shifts and the nausea vanishes, replaced by a comfortable and even exhilarating sense of orientation in their new gravity-free world. They learn to trust their eyes completely. This adaptation is so effective that it becomes the new normal. But this neurological rewrite creates a problem for the return to Earth. The moment an astronaut is back in gravity, the brain must rapidly unlearn its space-based rules and relearn the old ones. The vestibular system, which has been largely ignored for months, suddenly reactivates with a vengeance, often leading to a fresh wave of disorientation and imbalance upon landing. The experience of space adaptation syndrome is a powerful reminder that venturing into space is not just a technological challenge, but a deeply biological one, requiring our ancient terrestrial bodies to perform a delicate and temporary neurological overhaul just to function in a world without up or down. This grand cosmic dance of galaxies merging over billions of years is governed by a fundamental force that has shaped the entire history of our universe: expansion. And it is here, in the most precise measurements of this expansion, that modern cosmology has stumbled upon its most profound and puzzling mystery, a discrepancy so stubborn it threatens to rewrite our understanding of physics itself. This enigma is known as the Hubble tension. For nearly a century, we've known that the universe is expanding, with galaxies flying away from each other as space itself stretches. The rate of this expansion is quantified by the Hubble constant, a number that tells us how fast a galaxy is receding from us for every million parsecs of distance. Determining this number accurately is arguably the most important goal in cosmology, as it sets the age, size, and ultimate fate of the entire cosmos. The tension arises because we now have two supremely accurate, yet fundamentally different, ways to measure it, and they disagree in a way that cannot be easily explained. One method involves looking at the nearby universe, building what astronomers call the cosmic distance ladder. This is a step-by-step process that starts with measuring the distances to close-by stars using parallax, the same way your eyes gauge distance. Those stars are used to calibrate the brightness of certain types of variable stars, known as Cepheids variables in more distant galaxies. Cepheids pulse at a rate that is directly tied to their true brightness. By comparing their known intrinsic brightness to how dim they appear from Earth, astronomers can calculate their distance with remarkable precision. Then, by measuring the redshift of these galaxies, how much their light is stretched to the red end of the spectrum by the expansion of space, scientists can pin down the Hubble constant. This local measurement, championed by projects like the Hubble Space Telescope itself, gives us a very robust value. The other method peers back to the very beginning of the universe, to a time just 380,000 years after the Big Bang. This is the era when the cosmos cooled enough for atoms to form, allowing light to travel freely for the first time. This first light, now cooled and stretched into the microwave part of the spectrum, fills the entire sky and is known as the cosmic microwave background, or CMB. It is a baby picture of the infant universe, exquisitely detailed maps of this background radiation, provided by satellites like Planck, reveal tiny temperature fluctuations that are like frozen sound waves, encoding a vast amount of information about the universe's composition and geometry. By analyzing these patterns with our well-tested model of cosmic evolution, known as the lambda cold dark matter model, scientists can predict what the Hubble constant should be today. This is a forward prediction starting from the early universe and running the clock forward 14 billion years. The problem is stark and undeniable. The local measurement using Cepheid stars and supernova suggests a faster rate of expansion. The early universe measurement from the CMB predicts a slower one. The difference between them is not a small, negligible margin of error that can be brushed aside. It is a persistent gap of several percent, a discrepancy that has only grown more significant as our measurements have become more and more precise. Statistically, the chance that this is a simple fluke is now vanishingly small. This is the Hubble tension, two gold standard methods, each seemingly impeccable, yielding two different answers for the most fundamental number in cosmology. It's as if you used two different, perfectly calibrated rulers to measure the same table and got two consistently different results. This contradiction has sent shockwaves through the world of theoretical physics, because it strongly suggests that something is missing from our standard model of the universe. Our current understanding, which includes the effects of dark energy and dark matter, appears to be incomplete. The most exciting possibility is that the Hubble tension is a clue, a fingerprint of new physics, a phenomenon or particle that we have not yet discovered. The proposals to resolve the tension are as fascinating as they are speculative. Some theories suggest a form of early dark energy that briefly surged in the universe's first few 100,000 years, subtly altering the initial conditions that the Planck satellite measured, which would then change the predicted expansion rate today. Others point to the potential properties of dark matter, suggesting it might interact with itself or with other particles in ways we haven't accounted for. There are even ideas involving exotic particles like sterile neutrinos or modifications to Einstein's theory of gravity itself on the largest cosmic scales. While the solution remains elusive, the very existence of the Hubble tension is a powerful reminder that science progresses not just by confirming what we know, but by confronting what we don't. This isn't a crisis in the sense of failure, it is a crisis of opportunity. It signals a frontier of knowledge, a clear indication that our map of the cosmos has blank spots waiting to be filled in by the next generation of telescopes and brilliant minds. This discrepancy isn't a reason for despair, but for excitement, pointing toward a deeper and more complete theory of reality that lies just beyond our current grasp. But if the disorienting effects of space sickness represent a temporary challenge for the human body, a far more insidious and permanent threat has been discovered lurking in the microscopic world, one that could jeopardize the entire future of long-duration spaceflight. It turns out that the microgravity environment of space doesn't just confuse our inner ear, it can fundamentally alter the behavior of some of our smallest and most dangerous stowaways. Research conducted aboard the Space Shuttle and the International Space Station has yielded a disturbing finding. Certain bacteria, including well-known pathogens like Salmonella, can become significantly more virulent when grown in space. This means they become better at causing disease, more infectious, and even more resistant to the antibiotics we rely on to fight them. This phenomenon transforms the sterile-looking environment of a spacecraft from a safe haven into a potential breeding ground for supercharged microbes. The discovery was made through a series of elegant but alarming experiments. Scientists would send samples of bacteria into orbit, cultivate them in specialized growth chambers for a period of time, and then return them to Earth for analysis. In one landmark study, Salmonella bacteria that had been grown on the Space Shuttle were brought back and used to infect mice. The results were startling. The space-traveled Salmonella was almost 3 times more likely to kill the mice than identical bacteria that had been grown on Earth. Further analysis revealed that the spacefaring bacteria had undergone profound changes at the genetic level. Microgravity appears to act as an environmental stressor that triggers a widespread genetic response in the bacteria, causing them to switch on and off hundreds of genes. This response, known as the global gene regulator, pushes the bacteria into a state of heightened alert, making them more efficient at invading host tissues and more resilient against attacks from the immune system. So, what is it about microgravity that causes this dangerous transformation? The leading theory points to a phenomenon called fluid shear. Here on Earth, bacteria growing in a liquid medium are constantly subjected to gentle forces as the fluid moves and convects due to gravity. This subtle motion seems to influence how the bacteria behave and form communities. In the near weightlessness of space, this fluid shear is dramatically reduced. The environment becomes much more still and predictable. Scientists believe this low fluid shear environment is a key signal to the bacteria that they are in a unique situation, perhaps similar to being inside the stagnant, protected confines of a host's intestinal tract. In response, the bacteria preemptively switch into a more aggressive state, as if preparing for an imminent battle with a host's immune defenses. It's a frighteningly clever survival strategy, honed by billions of years of evolution, that is accidentally activated by the unusual conditions of spaceflight. This increased virulence is compounded by another worrying discovery. These bacteria can also develop a thicker, more robust biofilm. A biofilm is a slimy, protective matrix that communities of bacteria build around themselves, acting like a fortified city that shields them from antibiotics and disinfectants. In space, bacteria seem to form these biofilms more readily and with greater complexity. This means that a tiny bacterial colony growing on a surface within a spacecraft's water system or ventilation could become incredibly difficult to eradicate, posing a persistent contamination risk for a crew that might be millions of miles from the nearest hospital. For astronauts on a mission to Mars, a simple case of food poisoning could escalate from a minor inconvenience into a life-threatening crisis, as the offending bacteria would be more potent and harder to treat with the limited medical supplies on board. Addressing this microscopic menace is now a top priority for space medicine. Researchers are working to fully understand the genetic pathways involved in this virulence shift, with the hope of developing targeted drugs or treatments that could block this response. Some experiments are testing new types of surface coatings for spacecraft interiors that are inherently antimicrobial, designed to prevent biofilms from taking hold in the first place. Other strategies involve developing more advanced water purification and air filtration systems that can remove even the most resilient microbial threats. The battle against these space-enhanced pathogens is a silent but critical front in the effort to ensure human health beyond Earth, a stark reminder that the challenges of exploration are not always on the grand scale of rocket science, but can be waiting in a single mutated cell. But if the strange transformations of bacteria in orbit show how life adapts to new extremes, the stars themselves engage in a far more dramatic and violent form of change, a cosmic predation that unfolds over billions of years. Our next fact takes us to the heart of binary star systems, where two suns are locked in a gravitational embrace, and reveals a process as ruthless as it is beautiful: stellar cannibalism. This isn't science fiction. It's a common and crucial mechanism that shapes the lives of a vast number of stars, leading to some of the most spectacular fireworks in the galaxy. The story begins with a stellar couple orbiting a common center of mass. For a long time, they might live in a stable, peaceful relationship. But as the more massive of the two stars ages faster, it swells into a red giant, expanding its outer layers to a tremendous size. This expansion can bring it dangerously close to its companion star's gravitational influence. At this point, the balance of power shifts dramatically. The gravitational pull of the smaller, denser companion star can begin to literally steal the puffed-up outer atmosphere of its giant neighbor. A stream of superheated gas, mostly hydrogen and helium, gets pulled from one star and spirals down onto the surface of the other, a process known as mass transfer. The consequences of this cosmic theft depend entirely on the nature of the star doing the consuming. If the recipient is a main sequence star like our Sun, the influx of fresh hydrogen fuel can actually rejuvenate it, making it hotter, brighter, and bluer than stars of a similar age, effectively resetting its evolutionary clock. However, the most dramatic events occur when the cannibal is a much denser and more extreme type of star, a white dwarf. A white dwarf is the exposed, Earth-sized core of a star that has exhausted its nuclear fuel and shed its outer layers. It's incredibly dense, with a teaspoon of its material weighing tons. When a white dwarf is in a binary system with a red giant, it acts like a celestial vampire, siphoning off the hydrogen-rich gas from its companion. This stolen material doesn't simply merge with the white dwarf. It forms a swirling, flat disk of superheated gas called an accretion disk around it. Friction within this disk heats it to millions of degrees, causing it to glow brilliantly before the material gradually spirals inward and rains down onto the white dwarf's surface. It's on this surface that the stage is set for a titanic explosion. the accumulated layer of stolen hydrogen on the white dwarf is under immense pressure and heat from the star's incredible gravity. Eventually, the conditions at the base of this hydrogen layer become so extreme that nuclear fusion ignites, but not the stable, controlled fusion that powers stars for billions of years. This is a runaway thermonuclear explosion that tears across the entire surface of the white dwarf in a matter of seconds. From our perspective on Earth, a star that was previously faint or invisible suddenly flares into brilliance, increasing its brightness by a factor of 50,000 to 100,000. This is a nova, a stellar outburst that can be so bright it's visible to the naked eye for weeks or even months before gradually fading. The key to a nova is that it's a surface explosion. The white dwarf itself survives the blast. In fact, the cycle can repeat itself over and over again, as the white dwarf can continue to siphon material from its companion, building up a new fuel layer for the next eruption tens of thousands of years later. But stellar cannibalism can have an even more catastrophic finale. If the white dwarf is particularly massive and the rate of mass transfer is very high, the accumulating material can push the white dwarf over a critical threshold known as the Chandrasekhar limit. This is the maximum mass a white dwarf can support against its own gravity. Once this limit is exceeded, the star can no longer hold itself up. In a fraction of a second, the incredible pressure ignites carbon fusion not just on the surface but throughout the entire star. The result is not a nova, but a far more powerful, universe-shaking event, a Type Ia supernova. This thermonuclear detonation is so violent and so uniform that it completely unbinds the white dwarf, tearing it apart in an explosion that, for a few weeks, can outshine an entire galaxy. There is no remnant left behind. The star is utterly obliterated, scattering its newly forged heavy elements like iron, silicon, and nickel across interstellar space. These supernovae are cosmic lighthouses of immense importance because they always occur at roughly the same mass. They always reach nearly the same peak brightness. This makes them invaluable standard candles for astronomers, allowing us to measure vast distances across the universe. It was by observing Type Ia supernova in distant galaxies that astronomers made the shocking discovery that the expansion of the universe is accelerating, leading to the Nobel Prize-winning confirmation of dark energy. So, the process of stellar cannibalism, which begins with one star quietly stealing from another, can ultimately provide the key to understanding the fate of the entire cosmos. It's a profound chain of events that links the intimate dance of two stars to the largest-scale mysteries of the universe, a violent and creative force that both destroys suns and illuminates the deepest secrets of space and time. From the cosmic predation of stellar cannibalism, we return to a more intimate and symbolic relic of our own exploration, one that sits in silent testimony on the airless lunar surface. Those iconic images of astronauts saluting the American flag, its stars and stripes stark against the gray dust, are etched into our collective memory. But if we could somehow return to the landing sites of the Apollo missions, we would likely find a scene that is both haunting and strangely beautiful. The vibrant flags are almost certainly not red, white, and blue anymore. After more than half a century exposed to the lunar environment, they have likely been bleached a uniform bone white. The transformation of these national symbols into colorless relics is a powerful lesson in the unforgiving physics of the moon, a place where the conditions are so extreme that they can systematically dismantle the colors we take for granted on Earth. The primary agent of this change is the complete and total absence of an atmosphere. On Earth, our atmosphere acts as a protective blanket, filtering out the most harmful portions of the sun's radiation and moderating temperature extremes. The moon has no such shield. For 14 days at a time, the unfiltered fury of the sun beats down on the lunar surface, bringing temperatures up to a scorching 120 degrees Celsius. Then, during the 2-week-long lunar night, the temperature plummets to a frigid -130 degrees Celsius. The flags are subjected to this brutal cycle of baking and deep freezing over and over, thousands of times since they were planted. This thermal cycling alone is enough to degrade most materials, making them brittle and weak. But the real color killer is the solar radiation. Without an ozone layer to block it, the lunar surface is bombarded by the sun's full spectrum of ultraviolet light. UV radiation is notorious for breaking down chemical bonds, and the bonds in the molecules of dye that create color are particularly vulnerable. On Earth, we see this slowly in sun-bleached patio furniture or faded signs. On the Moon, the process is accelerated to an unimaginable degree, operating with an intensity that terrestrial materials were never designed to withstand. The flags themselves were not designed for permanence. They were made of ordinary nylon, purchased from a government supply catalog, and were essentially standard issue flags with some modifications. A horizontal metal rod was sewn into the top to hold the flag out, giving it the appearance of flying in a wind that does not exist, because a limp, hanging flag would have been visually disappointing in the photographs. This very design, intended for a dramatic presentation, may have also hastened the flag's deterioration. The constant, unsoftened sunlight would have acted most directly on the surface facing the sun, bleaching the dyes molecule by molecule. Given the intensity of the UV radiation, scientists estimate that the flags likely lost their color within a single lunar day, the first 2 weeks of their residence. The red and blue pigments, being more complex, would have been the first to break down, leaving behind the white nylon base material of the flag. What we picture as a symbol of national pride has for decades been a blank white standard, a ghost of its original intent. There's a poignant irony in this transformation. The flags, planted as declarations of a specific national achievement, have been effectively neutralized by the utterly neutral and unbiased environment of space. The Moon does not care about borders or politics. It subjects everything on its surface to the same relentless physical laws. This bleaching process is a kind of cosmic erasure, a reminder that our human symbols are transient against the backdrop of geological and cosmic time. It's unlikely the flags have physically survived intact. Besides the radiation, they have also been subjected to the blast from the lunar module's ascent stage when the astronauts departed. Buzz Aldrin reported seeing the flag knocked over by the engine exhaust from Apollo 11. Later missions planted their flags farther away, but they would still have been exposed to the intense vibration and potential micrometeorite impacts over the decades. They may now be tattered shreds or perhaps nothing more than faint, white stains on the lunar regolith. The fact that they are probably white transforms them from political statements into something more universally human, simple artifacts, fragile markers of a moment when humanity first stepped off its home world. They are no longer flags of a nation, but flags of the planet, faded by the same sun that shines on all of us, a silent and powerful testament to the environment that awaits any who dare to leave the cradle of Earth. And so we arrive at the final and perhaps most profound fact on our journey, one that connects every bizarre wonder and cosmic mystery directly back to you, the viewer sitting there right now. Look at your hand, consider the air filling your lungs, feel the steady beat of your heart. Every atom that constructs your body, every element that enables your existence, has an origin story that begins not on this planet, but in the cosmic furnaces of stars that lived and died billions of years before our sun was even a glimmer in the darkness. The iron that carries oxygen through your bloodstream, the calcium that forms the structure of your bones, the oxygen that powers every cell, these were not present at the universe's birth. In the beginning, after the Big Bang, the universe was a vast, simple soup of just 3 elements: hydrogen, a little helium, and a trace amount of lithium. The recipe for something as complex as a human being or a planet like Earth simply did not exist. Everything else, every element that makes life and rocky worlds possible, had to be forged in the most extreme environments imaginable. For millions of years, the first generations of stars, behemoths many times more massive than our Sun, burned bright and fast. Deep within their cores, under unimaginable pressure and heat, the alchemy of the cosmos began. Through the process of nuclear fusion, they smashed hydrogen atoms together to form helium. As each star aged, it would then fuse helium into carbon, and carbon into progressively heavier elements like oxygen, neon, and magnesium. This was a star's lifework, acting as a cosmic pressure cooker, slowly building the periodic table element by element. But these massive stars were destined for a dramatic end. Once they began forging iron in their cores, a crucial threshold was crossed. The fusion of iron does not release energy, it consumes it. With its energy source cut off, the star's core catastrophically collapses in upon itself in a fraction of a second, then rebounds in a titanic explosion known as a supernova. The violence of this outburst is beyond comprehension, generating temperatures and pressures so extreme that in a single, brilliant flash, it forges all the remaining heavy elements in the periodic table: gold, silver, uranium, iodine. The explosion then hurls this newly created stardust, this enriched cosmic material, out across the galaxy at nearly the speed of light, seeding vast clouds of gas and dust with the raw ingredients for new stars, new planets, and ultimately new life. Our own solar system is a child of one of these enrichment events. About 4.5 billion years ago, a cloud of gas and dust containing the remnants of countless prior stellar generations began to collapse under its own gravity. At its center, our Sun ignited. The material that swirled around it, rich with oxygen, carbon, nitrogen, and iron, began to clump together to form the planets. The Earth coalesced from this stardust, and in its early, turbulent history, these elements combined to form the oceans, the atmosphere, and the very rocks beneath our feet. Then, in a process we are still striving to understand, these non-living chemicals organized into the first self-replicating structures, kickstarting the long, evolutionary journey that would eventually lead to us. This means that the carbon atoms in your DNA, the nitrogen in your proteins, and the phosphorus that helps form the backbone of your genetic code all originated in the hearts of stars that are now long since dead. You are literally composed of their recycled remains. This idea, popularized by the iconic phrase, "We are all made of stardust," is more than just a beautiful metaphor. It is a scientific fact confirmed by spectroscopy, which allows us to read the chemical fingerprints of elements across the galaxy. It is a concept that connects us irrevocably to the cosmos in the most intimate way possible. The same calcium that gives a distant nebula its spectral signature is the calcium that strengthens your skeleton. The same oxygen that makes up the rings of Saturn is the oxygen you just inhaled. Every time you look up at the night sky, you are not looking out at a separate foreign realm. You are looking at your extended family, your cosmic homeland. The universe is not a place we are merely visiting. We are a part of it, a conscious, thinking portion of the cosmos that has awoken to contemplate its own origins. This final fact ties together every single one we've explored: the volatile moon, the diamond planets, the screaming chorus of plasma waves, the silent retreat of our satellite, and the impending galactic merger. All of it is part of the same grand, ongoing story of cosmic evolution, a story in which you and every living thing you have ever known play a unique and wondrous role. We are the universe's way of understanding itself, a collection of ancient stardust that has temporarily coalesced into a form capable of wonder, capable of asking the question, where did we come from? And the most astonishing answer is that we came from everywhere. From the profound realization that we are literally made of stardust, it's clear that this journey through 30 of space exploration's strangest secrets has been more than just a collection of trivia. It has been a tour of a universe that consistently defies our expectations, a cosmos that is less a cold, empty void and more a vibrant, dynamic, and often bewildering arena of infinite possibility. We began with the intimate, personal changes to the human body in orbit and ventured out to the volcanic heartbeat of Venus, the screaming electromagnetic chorus of planetary magnetospheres, and the silent, fading fury of Jupiter's great red spot. We've encountered worlds of diamond, moons with lakes of methane, and black holes surrounded by oceans of water vaster than our imagination can hold. Each fact, from the recycled water on the space station to the impending galactic collision with Andromeda, peels back a layer of the familiar to reveal the sheer, unadulterated wonder that lies beneath. This tapestry of oddities teaches us a crucial lesson about the nature of discovery itself. Space exploration is not a linear path toward a predetermined destination where we simply confirm what we already suspect. Instead, it is a continuous process of having our assumptions challenged and our minds expanded. For every question we answer, the universe presents us with 10 new, more fascinating mysteries. The Hubble tension isn't a sign of failure in cosmology. It's a beacon pointing toward new physics. The strange virulence of bacteria in microgravity isn't just a problem to be solved. It's a window into the fundamental ways life interacts with its environment. These aren't roadblocks on the path to knowledge, they are the path. They remind us that the universe is not obliged to conform to our intuition, and its greatest gifts are often the surprises that force us to think in entirely new ways. So, as this particular voyage concludes, the conversation is far from over. We want to hear from you. Which of these 30 facts reshaped your perception of the cosmos the most? Was it the haunting reality of Laker's sacrifice, the mind-bending paradox of a day longer than a year on Venus, or the beautiful inevitability of our galaxy's future merger? Did the image of a diamond planet or the silent, fading flags on the moon leave a more lasting impression? Share your favorite cosmic revelation in the comments below. Let's continue to explore this wonder together as a community of the curious. If this journey through the weird and wonderful has ignited your sense of awe, then be sure to subscribe and hit the notification bell. This is just the beginning. There are countless more mysteries waiting in the dark, from the nature of dark matter and energy to the search for life on icy moons, and we will be here to unravel them with you. Until next time, keep looking up. The universe is stranger than we can suppose, and that is what makes exploring it the greatest adventure of all.